Sure, go ahead
Yeah.
there.
Oh, okay. So interesting discussion, Emmanuel and you and Gerd. I think Christian
Oh yeah.
was there for a while, but I may have gone on vacation.
Yeah.
Um,
I'm surprised Christian wasn't more involved in the what was
yeah.
it called? Back and forth.
Yeah.
You
So
kind of quit. So that was okay though, because I suppose it was decent enough because like I think I was arguing with Gerd and Emmanuel by the end of it.
okay.
Like so if I had to like, well, no, it would have been fine.
Okay.
But yeah, when I say arguing, I mean
I mean,
debating.
you are going through the science, yeah, the scientific
Yeah,
aspects.
yeah. So it's interesting.
Yeah.
I don't
Yeah.
know.
So I had the last one was with the GERD. Then because I found that there could be extra dimensions in there. I was going to the last paper I had started about connecting to Kalabayo, the
Mm-hmm.
6-dimensional thing. So I
Mm-hmm.
found an interesting thing. I don't know. I had to check this one, but
Yeah.
right now my hypothesis how the whole graviton forms from
Yeah.
Calabi species. See, I had developed something called I think I discussed last time briefly. Time
Yeah.
field and space field. The sense gives the field to the time and space depending on the location. Like quantum level, only space it gives only to space, and mesoscopic gives to time, and um, time comes out of the transform because I
Well,
have the
that's pretty
transform, right?
interesting. There, what you're talking about, Rajan, because it relates to something that I sort of came up with a while back, where I was suggesting that I have to remember. I think I said time is like bosonic and
Oh,
space is fermionic because
okay.
like two different locations can't be in the same location at once.
Yeah.
So similar to fermions, but then so
Uh,
it's suggesting that time that like all moments of time are really the same as the next, which is
uh,
why eternity makes sense. Like
uh,
there's literally no difference. So I don't know. So then I'm thinking like you have fermionic fields.
mhm.
I guess there's like spin 1/2, and then bosonic fields can
Yeah.
be well they can be different kinds of spins, but usually
Yeah.
let's say spin 1 or something.
Yeah.
So then if you have a time field and a space field, perhaps you could relate them to fermionic bosonic fields, spin 1/2.
Yeah. Yeah.
Might be
Yeah.
interesting.
That's exactly what I came. I mean, kind of. So I came up with this description that
Yeah.
mesoscopic, you have the time comes out from the time is inside the trans. I have the perfect transform, right? So I can work with that, the
Uh-huh.
mathematics. So it's like a black box. So in the quantum level, the time is inside, uh, and the space field is always, it give the sense gives space field all the time except in superluminal thing. So the space field is there everywhere. The time field in the quantum level is inside the space field, but it comes out in mesoscopic level. And so I think we have some common factor what you have done, but let me describe some of the things that I come up with. So it comes
Yeah.
out in mesoscopic level, goes
Okay.
back again into astrophysics level. So again in astrospace there's only space field left. So what happens is, now you look
Yeah.
at the time. I mentioned about global, about what it called as a world line and timeline, right? So what happens is, another interesting thing is how the information flow uh,
Yeah.
also. So there's a Lagrangian point, let's say. That's a point of constant thing. So it connects with the world line and timeline, and then it connects to us, right? So it all forms like a manifold, which is like a kite. I mean, that's a complex manifold, like a kite, or um, it has like a curved surface, uh, but it can rotate because it's connected to this fixed point Lagrangian, right? It rotates, And in that rotation, so it has the fermionic, like you mentioned. That's where I think we have a common factor there. It forms the fermionic thing because it has now, you know, the 4 pi rotation, things like that. But when it rotates, what happens is it starts forming, it starts having, you know, I went to a description, I have written somewhere, but essentially it forms bosonic. It starts rotating and it forms 2 pi. And then you have like 6 of them like that. Like you have XYZ axis. So you have this manifold in all the, so you have in the x-axis x and minus x. So it forms like a cone, you know, but it's not really a cone, more complex surface, but you can imagine simple as like a cone. So you have cones everywhere, like X, Y, Z axis, cones everywhere. And these cones are now bosonic cones. And when they start doing rotation, they start precessing, like Thomas precession or something like that. It will have that. So what happens is that prevents complete rotation. So you have now the, you know, the solid angle rotation, but only the fermion can rotate the whole thing. The bosons can do half of that. And then the gravitons come because they can only do pi symmetry, you know, pi rotation. So the graviton starts coming in. Once all this manifold forms, the graviton is forms like a graviton. And now you have the extra space also because of the manifold, either Calabi-Yau manifold, essentially. It's a complex surface. And you already a complex surface, and then all the directions, you have highly complex manifold. That complex manifold is 6-fold. I mean, the 6-dimensional symmetry, 6-dimensional manifold, which is typically like Calabi-Yau manifold. And that is very complex because it's not a simple, you know, what you call as the cone, but it is a complex cone which has complex shape, typically like kite, you know, different shapes, and like your Mexican hat, things like that. You have to calculate that, but it is not.
Is it true that they are toruses?
Yeah, it could be toruses eventually. So eventually they form like toruses, but I don't know, Calabi-Yau manifold is more complex than a torus. Could be more complex because you have like a Mobius.
I think it's a torus, but there's, you know, let's say this is the torus. When you, it's been a while since I looked into this, but it's hard to describe. So let's say this is the top of the torus and this is the bottom of like one thing. You can push them through each other, so they go like this, and that's what you're seeing in the Calabi-Yau thing. It's actually is a torus, but the edges are pushed through each other, so you could like unwind them, make a torus, and then a 6-dimensional torus is very easy to create. We were doing that in our prime factorization. Remember the original? Yeah, the original one. I think we got up to I don't know. That was an infinite number of dimensions you could add to that, but I think we did like I can't remember, but at least 3 anyway. I think we go talking about infinite number of dimensions, and then you just say, "Oh, we did 3." No, well, at least 4.
Oh yeah.
Well, we never. No, yeah, we did. We went up to like 11 or something, but I think it's the computer starts getting very slow, and you know, so try not to go above 7 or something like that. But anyway, as you say, it's 6, so that's perfectly fine. And what was the deal? Yeah, the one thing that we didn't do was rotate the torus in the 4th dimension or in higher dimensions, because that would be an interesting thing to see. Because then you have the field like how did they say, where you're shifting the field kind of in space, so it's translating in like Y or Z, but then to have it, you know, and then you can rotate it obviously, but to have it translate in the 4th dimension, so rotating around the 4th axis of the, I guess they call it a 3 torus, don't they? When it's a 4-dimensional torus is like 3 torus, just like you have a 3 sphere, because it's a 2-dimensional surface, a sphere. So the 4th dimensional surface is four-dimensional sphere is a three-sphere, because the three-dimensional one is called a two-sphere mathematically. So, and that's the same then with the torus. So three spheres is a four-dimensional sphere. Torus. Three torus is a four-dimensional torus. So yeah. So, but then when you get into that area where the manifold is intersecting with itself, I think in order to do that, you need. I think there's probably a number of ways to do it. I've forgotten how they go about it. They don't use elliptical curved geometry, although that is related. I think they use something else. I'll just check. Elliptic curve. Oh, modular curves, the monster group. And you have these. So there's genus 0. That's where you have a modular curve with no aperture in it. So a torus would be genus 1, right? Because it has like one hole in it.
One hole? Yeah. Okay,
yeah. If you have two tori stuck together, then that would have 2. So that would be genus 2, I believe. And then genus 3. So how many yeah, I think that's how it works. Anyway, you get into all these prime subfields and super singular elliptical curves. So there's an idea, I think, that is this right? Okay, I'll keep looking anyway. So that's different. So have you been looking into magic squares at all recently? Or?
I have not looked at magic square. I thought that we had figured out this geometry and then the magic square will come, because I have previous publication, right? How the magic square comes into picture. I have a couple of publications. I started,
nice.
2 papers already there, peer review, where I go into a description of how the magic square is coming up. So we'll go through. I'm trying to put a paper now where we put everything together, kind of, But I just had to refer because there are too many things. But the magic square comes like you are consider a 0, 0, 0 matrix, right? That has automatically like a magic square in there, but it splits up, and I have given reason why it splits up based on signal to noise ratio, things like that. When you put a diagonal and cos diagonal, it automatically gets split up and it starts creating heterogeneous things. So what is 0, starts having something. So this is like an absolute genesis kind of thing. So why automatically it splits up? If you have vacuum everywhere, it splits up kind of. 0 is like vacuum, right? Suppose we start with perfect vacuum, then it's like 0. All the points are like 0, 0, 0, 0. But it cannot remain because it's magic square symmetry, but it's not a perfect symmetry. So it will split up to form, from magic square symmetry to heterogeneous things. So it will try to create points that become more like crystallographic symmetry type thing, eventually. So that's because there are 6 types of symmetries, right? 6 or 7 crystallographic things like cubic.
I think there's 7, is there?
Yeah, there are 7 actually. Yeah, I taught this course in the university here, ASU. Actually, the X-ray diffraction, called X-ray diffraction. So in that one, we consider that originally people thought it's 6, but actually 7, like you said, because 7 crystal structures possible.
But maybe one of them you could like take as the 0 point or the central point or something, and then so you could count 6 after that.
Yeah, it's a lattice. It's a lattice geometry, lattice crystal lattice. How the crystal lattice arranges itself, body centered, face centered, and all those different and triclinic.
Yeah,
and your symmetry reduces when you go up there, and it is like triclinic has very little symmetry. Like you talk about two-fold symmetry, four-fold symmetry. Like a square has four-fold symmetry, right? Whereas a rectangle, if you take
Oh
a
yeah.
Mobius
Yeah.
strip, rectangle has only two, what you call as the, two-fold symmetry like that.
Yeah. You're right.
So if you rotate it, how how it comes back to the same thing. That's what the symmetry is, right? So, and you go to more complex shapes, it will not, it will stop having even twofold. It may have only one-fold symmetry, something like that. But there are some things that is not allowed, like five-fold symmetry. You can prove, it's proved from group theory. And I was with another group in Penn State, and then that's very highly advanced. They work on that. But I attended. There are only very few people who know who are there, but I was able to understand and then that how you cannot get fivefold. But you said that Higgs something that you can get fivefold. They have proved now fivefold symmetry is possible, things like that. So,
well, in crystals, is it?
Yeah, in some crystal, you said that they have seen quasi crystal or something.
Yeah,
but group theory says that in real crystal.
Yeah.
Crystal, you cannot have fivefold.
What I'm saying about the fivefold crystal, yeah, they found that, and it's also quasi crystal. It's also sort of a projection of the 600 cell as well. So it's pretty interesting. What were you saying anyway, sorry?
We kind of, so
I think there's a delay, so sometimes we get.
Oh, no problem. So the real crystal, you cannot have fivefold symmetry. The group theory says, and I also proved.
Yeah, but then what is the quasi crystal if not a real crystal?
Yeah, quasi crystal is different. I think the fivefold symmetry is because, I think that eventually we didn't talk about that chirality or anything. I think it may have to do with chirality, things like that. Because you look at your hands, right? So you have five fingers. You can kind of simplify that. And you have already, you have to have a matching thing. So it's already a chiral thing, right? It's mirror symmetry is already there. So fivefold symmetry, eventually become chiral somehow. So you said that you can have left-handed one, not right-handed one, things like that, like particles. There are some restrictions there. So that may be that may all work together in the why the fivefold symmetry cannot occur. But quasi crystal could break that symmetry, so that may be the reason. So that I'm not sure.
I don't know. I'd say, I don't know. So they have their group theory proof or something that fivefold symmetry crystals don't exist, but then we see that they do exist. So obviously their proof is wrong, or
the proof is rotation matrix. It's a perfect thing that all the lattices, and it conforms to X-ray diffraction, the observable, the X-ray diffraction, electron diffraction. These two are slightly different. Electron diffraction is different from the patterns, So electron diffraction is different from X-ray diffraction. So you can do independent verifications, kind of, to find out. And there are many spectroscopic things, right? OJ and different types of spectroscopy. So from there, they have seen confirmation of this. The fact that real crystals with a proper lattice, lattice structure, that cannot have fivefold symmetry. They have actually, I think they have proved also. But that's different from quasi crystals. Quasi crystals break those symmetries. So, so I don't see any problem having fivefold symmetry in the quasi crystal, which is not a real crystal. It may not have proper lattice, So it is.
Oh, okay, right. So you're making a distinction between crystal lattice and then this other.
Yeah. So
but, you have. It is a crystal, right? Quasi crystal.
Well, it's like quasi particle. Quasi particle is not a particle, right?
Okay, yeah, but you're right. So you're saying it's in another classification, which is not straightforward crystal. It's in its own
unstable, stable crystal versus unstable, right? So quasi crystals are not stable crystals. I mean, there's nothing stable about it.
Are they're not going to explode on us, or what do you mean by unstable?
Unstable means, can it stay for a long period of time? See, there is no real stability of any crystal, right? Even crystals kind of break up, right? Eventually,
Right.
They don't remain like a cubic thing, like iron, for example. It has, let's say, base-centered cubic or base-centered tetragonal structure or something. You have a carbon. You need a carbon, right? So that's the problem. So a pure iron does not have any strength, right? So it needs carbon in there. So when you put carbon, it goes to the something called a tetragonal structure. So it goes inside and then occupies the tetragonal space. I mean, there are a lot of description, but I'm just simplifying.
Is that true? What do they call the iron when they put the carbon in it? Does it have a different name?
That's what the real iron is. Whatever iron we see, cast iron, like iron is created in a blast furnace, right? So your iron ore.
What do they call it when they? What do they call the carbon? Is it like called? Does it have a specific name in the process of?
It's called alloying. In general, it's called alloying.
But aren't alloys like a mix between different metals?
Yeah, metals also. Yeah, mostly. Yeah. So the iron, when they talk about iron, it has carbon in it, because without carbon, it cannot. Yeah. So even pure iron. Yeah, even an elemental iron like Fe, right? It's called elemental iron. It cannot exist by itself. Really, it will crumble into pieces. But it needs carbon in there, like interstitial, right, to keep it all bonded up properly. So
because I was watching. You heard about the submarine that went missing?
Oh yeah, right now they went to go to visit the Titanic. I mean, this is like a tourist thing, but it disappeared because of the implosion, right?
Yeah, there was an implosion.
But it was made of carbon, some fiber. It's a fiber.
That's right. It was a composite thing, and I was listening to. Well, I suppose I see your point, but just to explain where my thinking was going on this. I was listening to, the director who did Aliens.
Oh, what's his name?
James Cameron. That's it.
Oh yeah. I mean, he did a Titanic also. He did Titanic. And he has gone many times. He said he has gone many times there.
He has his own submarine and all that. So
he made his own submarine, and he said that's perfect, because they didn't test this one. He said that they didn't certify or anything. The other person also said, there was another person who came on TV who was, I forgot his name, but he also said that he is also a very high level expert, and he is actually a Navy submarine specialist or somebody like that. He also said that they didn't certify it, but the CEO, he said that, okay, let's go, because he was too excited. So he didn't blame him, but unfortunately he pulled the people along, and and then he also died.
Well, I think he thinks it's a tragic event all around.
Five people. Yeah. They all got implosion, because the carbon fiber said that the carbon fiber, they didn't test how much it can withstand the pressure. The pressure is enormous.
That's it.
So the carbon fiber was not tested whether it can withstand that level of pressure. So
obviously, the first time they went down with it was like tested in that sense, like it,
but he said that
the trouble is, each time it goes down, there's like water ingress and cracks can form, and they get
micro cracks.
The
micro cracks is formed.
It's like, how many cycles can it of like compression, decompression?
Exactly.
So he was saying that, like, when you build a sub, you build if you have like a cylinder, build it out of one piece, so that you can do finite element analysis on it to see what stress it can take, and then how many cycles it can take, and so forth. And then you don't use it after before
so many cycles
of failure.
Fatigue. I have done a little bit of fatigue testing, but
oh, great. But
Some of my
so
friends.
this idea of he was saying that you cannot do a finite element analysis test on a composite material, was what he was saying. So
Well,
this,
they're not developed the thing. I also studied a little bit because I
yeah,
took a course on
yeah,
finite
yeah,
element a little bit. Uh,
great,
I am not going to advanced level, but I know how it works. Like it has
yeah,
nodes and all that thing. You probably know it. That was a long time ago.
yeah,
I know the basic concept in that.
yeah, me
That's
too.
a wonderful thing because civil engineers, structural engineers, they use it. They very, very most used thing, a most useful thing. Finite element is one of the most useful models,
Yeah.
and it can capture a lot of things about the stresses, strain,
Mm.
and how the structure stands, everything. So
Well,
I
you
think
see that
that's
on trains a lot as well. You know those diagrams where it's like a triangle and
uh-huh,
then a line,
uh-huh.
and then sometimes the line is like this or something, and there's a circle
Yeah,
on
yeah,
top.
yeah,
It's to do with shear and shear stress and
yeah, yeah.
yeah. But I
So,
don't understand. I don't understand the code. I just used to look at the pictures, going, "What do they mean?"
oh yeah.
I
The
assume
problem,
like then it's shear or something like that, and so on.
yeah, shear. You are tensile stress where you just pull it, right? Something
Yeah,
like
yeah, the bending, and then the
yeah,
shear stress is at the edge or something where it snaps.
yeah, shear stress. So it's a axial, triaxial things. So are you going, which axis you are bending it, like your torsion field, things like that, right? Because some axis you have moment of inertia, okay, momentum, right? Momentum axis. So it will
Yeah.
start rotating and it create rotational things. So shear is like a surface thing. The whole plane gets warped. Uh, so it is like shear is like between two planes, let's say two planes, and they move against each other, like shear stress.
Yeah.
Like tensile is you pull it along that axis, of whatever the stress axis is, the strain. So the strain will be uniformly increasing, whereas in shear it's the whole plane. So tensile strength is like the one dimensional, you can say,
Oh, okay.
whereas shear stress is like two dimensional. Torsion
Yeah.
is like three dimension, the simple way.
Hmm.
It's more complex
Okay.
than that, but the simplest concept will
Yeah.
be simplest
Okay.
way to understand it.
Yeah.
So
Yeah.
it's a
For sure.
because I
Definitely.
understand about dimensions a little better. So in that sense, I can imagine how that works. So I simplify that. But when you actually study, you have modulus and things like that. You have
Hmm.
Young's modulus. You have the shear modulus. You have modulus for each of them. You know, uh,
For sure.
modulus. Yeah, modulus is like you multiply that modulus by the strain, you can get stress, the stress and strain relationship. So the
Oh,
modulus describes the relationship. So I have used I have used tensile strength a lot. I have not used shear stress in my corrosion, stress corrosion, but I have used quite a lot of the tensile strength, tensile stress, because I developed even some small instrumentation to do uh, you know in the lab from my advisor, and then I did it at small level. I created a small thing for scanning tunneling microscope, things like that. So I micro scale. So I converted the macro scale to micro scale. So I had to know the concepts, the whole thing. I kind of recalculated everything, and then
mm,
it worked, and it was working. So I was quite interested in those things, so I developed my original way, and it was approved by the Department of Defense. I was working a project on that. So, but
mm.
once they get that thing, they let you go. That's what happened to me, because it was so perfect that anybody, it can be recreated very easily. So, but the company got the patent. I didn't get, like that. I was working for the company, and everything got folded up, because it was like a Star Wars program, but it got folded up after, uh, the Iraq war. After the Iraq war, they kind of dismantled that, and then they gave it to other agencies, things like that. So then I was let go, and I went through the financial crisis myself, and then I was teaching in ASU. So all this, my background, but now I'm with our thing and coming back. That's why we want to rebuild the whole thing. And now finally we attended a conference, and so it was a ground zero level. Now we went to phase 1, phase 2. But the idea is that the concepts, I forget because it's so complex. Like I studied thermodynamics, right? I was watching Sabina Hossafield's thing about entropy yesterday. And I like her thing because it is not a long thing. It's like 20 minutes, 15 minutes, 20 minutes. And I like that type of thing because I don't have much time to go for hours together, sit together. But she gives us snippets of the things, and she analyzes the whole thing completely, like entropy, second law of thermodynamics. And you should watch that in like 17 minutes, I think. Why the entropy thing is not may not be that way, and she explains nicely because I had taken one of the highest courses when I was doing my master's PhD graduate study in thermodynamics, called them 500 level I had taken. So I don't remember all of it, but a lot of math involved, Stirling's formula. But there's a simple formula. The entropy is Boltzmann constant times natural logarithm of omega. Omega is the microstates, how many microstates it can have. So you have microstate and macrostate, right? So she has gone into particle physics, and that connects with the particle physics, and it says that there is only one microstate possible in the whole universe, So if you put gamma omega equal to 1, it becomes 0. So entropy will be 0. And then you have the macro state. We create the macro state, like all the particles. Let's say it goes to one side of a container, right? Suppose it goes all the way to one side. So the entropy there will be much higher, because entropy is what? A disorder, right? That you put some particles there and start going everywhere, right? Like ideal gas law. Ideal gas law, nothing stays static. So any time it will start vibrating and they hit against each other, like I mentioned last time about the fundamental equation, like mean free path, things like that. That there's a nice thing, calculation about that. 8 pi mt cubed or something like that. M cubed, constant sum, and then it relates that's how they get the temperature. And the Boltzmann constant is very closely related to that. Boltzmann calculated that from there, and then verified with the calorimeter and things like the experiments. So they came up with a nice equation for temperature. Energy and temperature are related, simply by Boltzmann constant times the absolute temperature, things like that. So actually, we derive that in that thermodynamics. We derive that. So you have microstate ensemble. She didn't go into those details, but I remember now ensembles, and you say microstate, how they add up to microstate, and how the disorder comes. So you are describing the whole disorder, because there are many configurations, right? When it hits, so it can go this way, XYZ axis, and you analyze. It's not an axis analysis, but actually calculations, more statistical thermodynamics and things like that, calculation. So that calculation. So she was explaining that the whole universe, there's only one micro state, but they form macro state. That's what we see. So if it gathers one side, you can put a ball like in a piston, right? That's what we use. So then it can push against that. And so the entropy, what happens with entropy is that you have lower entropy, like energy, pure energy has very low entropy, right? Like electromagnetism, things like that, or any other pure energy states. But it's like a minimum noise, right? Whereas she didn't say exactly that, but I can easily connect with the noise and signal. So the lower the entropy, the higher the pure energy and less noise. So signal to noise ratio will be much higher. Whereas high entropy have more noise because it's going all over the place, and it has very low energy, useful energy. Some call
Yes.
the work. You call the work.
Mm.
Uh, the work is a useful energy. So this one can push this you know push this piston. That's how we get, like, we use for car, for using in cars, things like that, internal combustion engine. So when you combust, you have the high energy fuel that is created, and that has molecules all over the place, and it has very high kinetic energy, and it will push this way. So essentially, that's why, if you have one place, she explains, if you have air, why air cannot be in one place. That's a good thing for us, right? Because we need air. Air cannot just accumulate. There's a room, it cannot accumulate in one corner of the room, right?
Yeah.
It immediately diffuses or spreads out because the entropy. You do the
Mm.
entropy calculation, it'll automatically spread out. So then, everywhere it's the same. It's called equilibrium, right? We call it equilibrium. So
Yes. Yes.
yeah. So it's a very simple things, but she explains nicely. And from there, she says that why entropy of the whole universe, why the disorder. See, second law says that the entropy keeps increasing, right? The disorder keeps increasing. That's what second law finally says. The entropy of the universe is increasing. Essentially, that's what it says. So she said that why it cannot be that way. Because when you calculate microstate, is the whole entropy of the universe is zero, because log of omega is one, so the entropy is zero. So the only thing is difference is that some places here high entropy, some places low entropy, right? And she didn't
Yeah.
connect with a single source, but we can easily see, like John's idea about about the what you call the source and sink, right? The source has very low entropy, right?
Mm.
And then sink has higher entropy, so it moves there, for low entropy to the higher entropy, and then everything starts equilibrium. So the flow will occur, right? So
Yes.
so you have the flow from higher entropy, low entropy to high entropy, because the energy will be thing. So she, and she agrees that it's confusing little bit, because exactly happened, but only we can understand in terms of useful work and heat and energy. We can
Mm.
understand that, because and I agree with her, because I can understand from heat. I know that suppose I useful energy, when it becomes heat, it's become very less useful, right? We cannot tap that energy. So
Yes.
from that point of view, you can understand. But then you understand that entropy is just the opposite. So heat has higher entropy than pure energy. So you have to put it on that scale, then it's easier to understand, you know. So I think that's where the confusion comes sometimes, entropy and this thing. But you have to straighten out, like even Hawking's, Hawking thing, uh, black holes, they calculate the temperature, things like that, right? So the temperature essentially is a measure of the heat, right? Heat content. It's a measure. So whenever you have higher temperatures, the entropy is higher, should be higher, right? So putting that in perspective, I think we can understand, it makes sense. Because there are a lot of things based on this, like transformations. Like I study I did study all of it, but I study very high level phase transformations, and how the entropy is involved with that. There are a lot of
You're talking about the phases of matter, yeah?
phases of matter, like even solid things, right? You have solid, like iron, I said, right? It go to bring out temperature, it goes to different phases.
Yeah.
You have
You have
you have
those phase diagrams where it shows
phase
where,
diagram, yeah,
yeah.
highly complex phase diagrams, like
Yeah.
3D phase diagrams. We had to do that because I was specializing in that. So it's called physical metallurgy, where you
Mm.
go do the things. I don't remember all of it, but even at undergraduate level, I have studied that. At graduate level, I used some of it even for my
Mm.
research, because my professor was one of the top persons in physical metallurgy. He was really good. One of my advisors. Other
Okay.
advisor was physics. He was from Harvard
So
physics.
That he was from
All this,
Harvard. Where did you study again?
called Case Western. It's an Ivy school. It's like Cornell. You have heard about Cornell?
Yeah, it's
It's
Ivy
very
League, isn't
similar.
it?
Ivy.
Ivy
It's
League.
called Ivy League. Yeah, they are the top. They are, they are highly specialized, high level professors are there from
Yeah, yeah.
MIT. My
Yeah, I mean, if you
chairman
had
was
a
from
high level
MIT.
professor, you it must have been a. It's obviously going to be a high level college, right?
Yeah, it's a high level. So people are not heard about it, but if you remember where they measure the speed of light, right? It was in my the first I was there, the university I was, Case Western.
Wow.
It's Case
Oh, very
Institute
good.
of Technology. If you look at the institute where they were, right, where they measured the speed of light, um, you know, that's where it was. That's my
Cool.
university. There, I did my graduate study. So there are high level people. Like the chairman was from MIT originally,
Yeah.
MIT, and then but that
So,
botanics professor, he was from Cornell. You know Cornell, right? Cornell
yeah,
University.
yeah. I've heard of all
Yeah,
of the. Well, a lot of them. Like I haven't heard of the one you were at. But that's. I mean, there's hundreds of these universities, isn't there?
yeah. Because I don't know why. Because it changed from Case Institute of Technology to
Hmm.
Case Western. I think it became more like art. They infused a lot of art in there, art, humanities, and art courses.
Yeah,
So
yeah.
that they combined those together and became Case Western University. So people don't remember,
Okay.
but if you look at deeply,
Western Reserve University, Cleveland, Ohio.
yeah,
Okay.
you look at the people who measure the speed of light. See,
Okay, I'll check that out
values.
later. Actually, what I'm
Yeah.
gonna do now is I might share I just share some stuff
Okay.
that I that we were talking about it earlier. Um, just let me find the. I go to present. uh, this is going to be in a very haphazard kind of way.
It's okay.
Hopefully, okay. Window, entire screen we need, and share. Okay. I think first is maybe this. No, not that. So this is what this is what we're talking about. Elliptic curves.
Oh,
Yeah?
oh,
So
I see.
even this goes through here and that goes through there. I think that's kind of what happens. I'd need to look that up, but this is a two-dimensional elliptic curve.
Okay.
And then you can have another two-dimensional one
Oh, you're
here. You see
rotating it.
well, no, this is just as you change the coefficients, the
Ah,
bubble here that's
ah,
kind of forming sort of can break off if you like and form a circle.
I
Like
see.
I got rid of those lines. It's just
Oh, it breaks up like a bubble, like a water bubble, for example. How it it's
yeah,
called necking. It's called necking. You can calculate the
yeah,
stress. We
right.
actually we have mechanical metallurgy also, where the
Oh,
professor
okay.
proves, and then I took that course, fairly high
Yeah.
level, and you
Oh,
can prove that, yeah, how it splits up, how
this is
stress.
it. So I was interested in making a 3D
Oh,
version
nice,
of this.
the nice graphics you have showing
Yeah,
how it split, how it separates, how the bubble
that's it. Yeah,
separates.
yeah. So I wanted to make 3D versions of the
Oh,
process of how it breaks up.
that's
I think
nice. I like this one.
you can use a slider, I think, to change. So there's no or
Oh, it's a continuous
yeah,
simulation of how it happens.
yeah. You can actually move it. Oh, hang on a sec. Maybe like I don't know.
Different stages of
Yeah, there it's connected. You see, and
still
then,
connected.
right, but then you can move it. I think if you move it further, does this?
Do you use an equation or something to do this, or just
Yeah, it is. All of this up here. This equation, I think.
oh, that's there in the equation.
NO times z to the power 2 minus n1 times y
That's
cubed.
from
So
the
it's
Google. You have it in Google. This. How did you get this equation?
yeah, it's like a standard equation for elliptic curves, I think. Well, no, it
Oh,
wouldn't be standard, but it's I don't
Oh,
know.
and then you
Like,
coefficients. You change the coefficients. Okay.
yeah, like there's particular rules about elliptic curve geometry. It always has to be like a power
Oh,
of
that's
3
nice.
or a power of 5,
Oh yeah.
and then you have minus x times. So it's like they're really specific. But if you want to make 3D
Yeah,
versions
simple
of them,
equation. Yeah. You have the simple equation of x over y and x square or y, something like that for
yeah,
elliptical
here you
things.
go. This is also simple one up here, you know. So it's like x squared plus
Yeah.
2x plus 1 plus
Equal to
y.
y.
Yeah, equal to y cubed, exactly. So it's the cubed is the important part, I think. So anyway, I was attempting to make more and more of these how do you say, elliptic curves. And one thing you notice is that you can make them so that, I don't know, it looks like an anvil kind of. Like you can imagine if you're coming up, this is like a cross section of an anvil, and then when it connects to here, so it's like you can basically see the whole thing as a shape. But then if you connect both of the anvils face on, you create this thing, which is yeah, exactly. But and another one here. So and then if you look at this line here and this line in the center there, the aperture, it is this line and this line, yeah. So the point I'm making is you get the elliptic curve back from the 3D elliptical curve, and then there's another one, this and this. In fact, this here is the equation for this. So how do I switch them back on? There's this line here. You can take a line through, a plane through, and that plane then, the intersection is an elliptic curve. And I can switch that one on. I can turn this one on. And this intersection, again, is another elliptic curve.
Okay.
So we could like move the plane back and forth through the 3D elliptic curve to create.
It's a nice animation.
Yes. Well, this is part of Grapher from I forgot what they're called. Apple made it. So if we go in here, I can do the same thing here. You see, so so these lines here are the same as these lines here, I think.
Okay.
It's been a while.
It's a three-dimensional version. Three-dimensional.
Right. Yeah. But so it's a three-dimensional version that creates sort of an infinite number of these.
Okay.
Kind of. I'd have to look into it. But so going back to what we were saying about the Calabi-Yau surface.
Yeah.
So you see here, this is a torus essentially that's squashed, and you can get it so that the top part of this torus is supposed to wrap around, yeah, but for whatever reason it didn't. But you can get it so that the top part here goes through the bottom part here. I just can't remember how to do that. You have to move these lines or something. So I'm going the wrong way by the looks of it. I think I might have changed the equation. So, there we go. Getting closer to it. See what I mean? We're going to eventually cross over. I think I might have changed the equation to the point where it's not possible to get them to cross over anymore. Oh, look at that. It's pretty cool.
Wow. It's like a fan.
Or like a flower or something.
Yeah. Or like a fin. Like a fin.
It's nearly, yeah, you see, I think something's gone on with the equation. It looks like a palm tree or something as well.
Yeah, like a fan blades. Or
yeah, true, yeah, interesting. So let me just see. That's when it's at 0, so maybe we've gone too far. 8. So I think it's kind of crossing over there. Anyway, so like I said, I may have produces a nice shape though. These are ring cycloids.
So you can construct the Calabi space from here, from this one.
Kind of. You could if
like
you
a Mobius strip. Yeah, it's like a Mobius strip.
Equation.
And you rotate it.
But I mean, it is giving some pretty.
Yeah, nice, this is what I was thinking. kind of the shape I was telling, like kite and fan, things like that. So it's
Oh,
very
great.
close to what you are showing. So you already
Oh,
have it.
yeah. You can see there. You can see the kind of well, yeah. I mean, I haven't even really experimented with a lot of this, so. But I mean, a lot of the results are quite similar, actually. Let's turn them up to max. They've got a completely different. Kind of going back to the original shape that we were at, really. What happens if this goes to max? I think when they just max out, it just becomes quite boring.
Ah.
Oh, well, maybe not. Oh, it's done something completely different there. That's nice, actually.
Oh yeah.
Maybe I'll put this one back down. I mean, you could spend all
Actually,
day.
I came up with like spiral. I was solving some problem. I was sorting. We'll talk about later, but yeah, your
But yeah, so
spiral.
these are more ring cycloids. So this is a ring cycloid.
Ah, cycloid.
Yeah, it's again, it's just a simple equation. One of these. Well, it's not that simple, actually. No, it's not simple at all. But I got that from Wikipedia, I think, and Dupin's cycloid. This is someone else's work that I was borrowing. It's like an example of a
cycloid, you are cartoid, cycloid, all kinds of things like that.
Right, and then you can ring cycloid.
Spiral.
Pretty cool stuff. So there's like a torus that kind of crosses into itself.
Wow. So this is the one you're talking about, two toruses coming together?
Kind of.
This is a simple strip of that, like a Mobius strip of that.
I'm not sure. I think it's more this one where, yeah, I think they're related. I mean, I think this one and
if you rotate it, you get that.
This one, when you start changing some of the values, you eventually get. See, this here is like an elliptic curve as well, because this small ring here, and then the larger one. So when this goes to infinity at the back, you get this.
Oh,
essentially. Okay. So it's a Clifford torus, you know. So if I switch off these lines, which are kind of confusing, this is the inside of the torus, and it wraps around that way until it comes to the back. So that's, and then the other inside, because you know the way a torus is double, is this, and then this wraps around the outside this way, which means that this entire thing is a torus that's being stretched four-dimensionally.
Like a black hole. Black hole or wormhole can have something like that.
Yeah, that'd be cool. So another thing I was attempting then was to make a 3D version of it where you could actually pass the these are the two planes that are on the other side. So this is it, and then when the plane, you could move the plane, and then it would output. The idea is it would output a two-dimensional elliptical curve, and the equation.
So they can flow into each other like four-dimensional, and they'll come out. So there is no discontinuity there. So it's continuous. Well, it can come out on top, then come back on the side, come back, right? So it has a
well, not really. No, this is all three-dimensional.
It's all connected.
You know the implicit, explicit diagrams.
So you rotate this in 3 dimensions, 4 dimensions.
This entire thing. This is all 3D. This is all 3D, but and same with the cycloid that I showed you down here. This is all 3D. But I'm saying that there is a way to transform all of these things in 4 dimensions, and halfway between the transformation. So this looks like it's getting there, but then this will at the back it will open up and it will wind up looking like this. These shapes are still all 3-dimensional, and so that is why. Excuse me. That is why this is 3-dimensional. You see, this is the same shape as the green one I showed you earlier. It's just harder to see that there's meant to be a hole here, but
there's a hole.
You can't see it. So I think we can shift the y coordinates. Oh God, what happened there? It's been a while. It's been a while since I looked at this.
Something
So
hanging out there.
oh yeah. So when you change the y, and this is changing the value of the elliptical curve values. Or am I saying that right? Yeah, the 3D elliptical curve values. So I probably should. Maybe I should run this again and get back to the. Will it work? Oh yeah. So if I just.
So each one changes the coefficients.
Oh, but
we move it.
Yeah, that's right. So this changes the coefficients, and this should change the XY axis of the plane as it cuts through the elliptic curve. But for some reason, it's not working. It's been a while since I looked at this, so excuse me. There may be some an error may have crept into the code somewhere along the way, or. But oh yes, the idea is, sorry. The idea is that those planes, as they intersect that that elliptic curve, will produce these, and then the idea was to reverse these using modular forms. So you get the modular equation of these elliptical curves, and then
I see.
Yeah, so and then there was going to be connecting it maybe to string theory and particle physics. But,
wow.
Yeah, but in the end, it all turned out to be a bit too difficult. So I put it on the back burner. There was the reason why. Let me think. Can I just change it a bit? Okay, that's good. So I really don't know what these do anymore. I'll have to look at the documents to see. And it doesn't seem to be moving. And if I change this. Okay, I think no matter what you do, it just kind of changes. I mustn't have put in the code for the planes yet. Anyway, it's a bit tricky. So yeah, the trouble is trying to convert the elliptic curves. It's easy to convert from modular forms to elliptic curves, but it's very difficult to convert backwards. I can't figure out how to do it, so that kind of ended.
Like inverse transform, yeah, inverse transform.
I don't know. I mean, if you can figure out how to do it, let me know. But at the moment,
it's probably inverse transform. You have to change the x and y coordinates. Essentially,
oh, I don't know.
It's not easy. Sometimes not easy.
Well, what I've been using, I was using something called Sage Math. Is it Sage Math? And they make it very easy. Like, it's very easy to convert between an elliptic curve and a modular form, but it's not so easy.
The modular.
It's not so easy the other way around. I mean, you just get lost in these loops of trying to find. And I'm not. I mean, it is possible, but
your square roots, they are disconnected, right? So
sorry, what?
They disconnect. The modular means they are disconnected, right? Disconnected entities.
The modular things are to do with. Just let me fit.
Like you saw.
Do you know the guys, the modular forms, the Mobius transformations?
Yeah, Mobius.
Right. Yeah. So those they use that. They have the SL2C and Poincare group with you know, that whole the sphere. I think the block sphere, but more Poincare and the Lorentz transforms in relativity. So then you have them in quantum mechanics, relativity, and so this seems that was the big thing of representation theory was, oh, we have these matrices for relativity, we have these matrices for and groups, you know, for quantum mechanics. So oh, right, we'll try and join them together, and then, you know, so I think it's been a failure.
No, yeah, because there's a fundamental problem, observers, things like that come to picture. And I think your thing, I think I remember briefly, it's a high school, sometimes I teach that high school math. There's something called net, you know, you form a net. And it's a very complicated thing, the geometry. You have to form a net and you have to find the net. And then the net can be used. I think that's the intermediate thing between the modular uh, and your elliptical curve. Maybe a net. You have to find a net. You have to look up the geometry, how to find a net. It's a little bit complex.
Oh,
but
do you mean like a map between the two?
Yeah, map between, called net. So
right,
you find,
interesting.
So they are like,
is that a category thing where you got this like kind of like a surface between the two or something? Or?
Geometry, basically fundamental geometry, where you form, for example, I think it depends on the perspective. You have the elevate, you have like they use for in civil engineering, right? You look at the elevation, called elevation. You see the plan. You look at the side view. So different perspective of the geometry, you know. So you get the two, you convert the 3-dimension to 2-dimension. So you look at from here. Suppose I look at my wall here, the net will have the cycle complex. So the net will have like you can put a rectangle here, and the rectangle will have a line in there. You know, that's the simplest net. So you form an so that gives a 2-dimensional projection. It's like a projection.
Is it a projection or is it a cross section? Sorry.
It's like a perspective. So I look at like that. It's called, I may call it elevation. So you look at the elevation, I get like a rectangle here and like that, and the line that goes in between, right? But if I look at from top to bottom, right? If I look at on top, imagine it down. So I get that. Now I get like two lines, perpendicular lines, like that. I get like that from top to bottom, right?
Yeah. Well, that's your ceiling and the wall, yeah.
Yeah. If I'm able to see,
yeah.
Suppose this
that is a cross section, though. That seems like a cross section. But
yeah, it's a different view. It's a different view.
Yeah,
so
that's kind of still perspective. Well, that's what I'm looking into a lot with the sort of perspectives being important from the point of view of transformations and this kind of infinite. I noticed, you know, Emmanuel's stealing my thunder there a bit on what's the name of that? Stack Overflow, because I came up with this idea where you could have like infinite speeds because of projections.
Oh yeah, it's a nice thing you are talking about geometry.
And then he's saying the same thing, but he's using, I think he might be using a different equation, or I'd have to look into it. Because I was just talking about it from the perspective of oh god, the Heisenberg uncertainty principle. But I also have it in previous papers to do with entanglement and, you know, basically my thing is like the fourth dimension, you know, like I use that to solve everything, because why not?
Yeah. So Sabina actually talks about Heisenberg. It's not exactly what people think it is. You know, thing is that it doesn't mean that you cannot measure. Suppose you are measuring like delta x, delta t. Suppose you measure very accurately the time, right? Delta t. You cannot have that accuracy with delta x. That's all it means.
Yeah.
Suppose you are able to
measure. I think it's like excuse me, it's kind of complicated in the sense that well, you know the way I mean, I'm really not prepared to discuss the Heisenberg uncertainty principle in any great detail, but let's say you have the you want to find the momentum exactly, yeah, and so the position becomes the wave, the Fourier kind of transform of the wave means the wave spreads out, and it seems to, you know, it could go to infinity, I think, from a mathematical perspective, but well, really, it goes, and then it will eventually reach the zero line. So it's not like infinite. But I think there's probably a place in the mathematical equation where the line should be infinite, or like infinite to as far as we're concerned, you know. But yeah, I know what you mean. But the point of view also is that the whole thing I'm coming at is from like that there's this perspective where things are projected from, you know. So viewpoint is important or something.
Yeah.
Which gives the idea of like why consciousness may be important, or detection, or any of these things.
That's why I call consciousness.
So once you have this like projective point at infinity, or the opposite, the origin point, and the projective point at the origin, which I think is probably more important, and that's never factored into the equation, which is interesting. You know, it's always skipped over. So it just is like you might skip over consciousness and say, well, we're not going to include that in the equation, because even though it's actually the most fundamental point of the entire projection, it's just a point at infinity that we can't calculate. So we skip over that. But then there's other points of infinity that we can calculate, or that we prefer to calculate, which are the projective points at infinity, which are just useful for like any number of things. You know, that you could like, anyway, we've discussed that previously, so might skip over that. But what were we saying about the Heisenberg uncertainty principle?
Yeah,
they talk about different. So you have the momentum and the position, or you talk about the time and the energy, or any like two things. But then it seems to get lost a bit that they're saying, oh well, like you could talk about that you can apply it to any waveform, like, because then you have the wave space, or the domain, and the frequency domain, and the other domain was a position domain or something.
Frequency you have domain, frequency and time domain, frequency domain.
Right, thank you, yeah. But that analogy isn't really correct. I mean, you cannot say that the frequency and time domain are analogous to the momentum and position. I don't agree with that personally.
That's why I do legender. See, in my transformation, like I said, 20-page derivation, right? I take into account all that. When to apply, because at that time I was thinking correctly. I think the most correct way of thinking. I know it's perfect, but I know I applied correct way how to transform time domain. So I use Fourier when I have to transform between time and frequency, and you use legender. When people really use this one. I use legender when you transform from your momentum, your space and time, things like that. So the velocity, the momentum velocity, and all that. And then you use Laplace when you have flow and things like that. So I used correctly, and most correct way. I would say, you know, I'm not 100% correct, but the most correct way. But I found that you have to use some tricky math. That I think I did it correctly. The best way possible, ever possible. So the 20-point derivation is, because I believe in derivation. You know, derivations are step by step, so you can go back and check, okay, and you cut the step. But the theorem and proof doesn't. You know, I had done that in high school. I was pretty good, but I think there is a problem, like a disconnect. It's like a modular thing. Theorem and proof are modular thing. You know, you can think of that way. They're separate.
Theory and proof.
Theorem.
Oh, yeah.
Like mathematics theorem. Like
I think it's kind of like a deep sort of what would you call it? It's like a philosophical thing to do with larger categories within science. That's pretty interesting.
Yeah.
I mean, that's an interesting way to go. I think that might be a different almost subject, though. It's like, how do our systems within science work? And it's pretty cool, I guess. But same time, yeah, maybe there's like a difference between that and like maybe the actual thing that we're researching, the particles and the interactions and all of that. So one thing I was thinking was the I think there were, the idea where you have like let's say an observer effect, such as
Yeah.
the little slit experiment or something. And I think the way I've forgotten how Heisenberg initially introduced the concept of uncertainty. I think it was something to do with, it wasn't flow, but it was like change, and it doesn't really matter. But the point is that initially I think people were thinking about it as a kind of observer effect. So if you were observing the position exactly, then the other thing magically kind of goes to infinity. But if you're observing the momentum perfectly, then the other one goes to infinity or close to, or whatever, or it just becomes very uncertain. So they're saying, no, it's not an observer effect. It's actually related to, I think they're saying it's related to the Fourier transform, and that this is just a general thing. Like if we were to select any frequency in the time domain, we get an infinite frequency in the frequency domain, right? Because it just spans infinite. But it's just not, it's not correct. I mean, you cannot, I don't think you can, obviously the Fourier transform is used in the Heisenberg uncertainty principle, but it's not the straightforward way that it in time and frequency domain. And you cannot say that these things are the same. And that just because there's no observer in the first one, therefore there's no observer in the second one. That is completely wrong. It's like they are desperate not to have the observer in the system, because they're worried that if all of these scientific things require observers, then that makes consciousness an integral part to the universe, which philosophically, anyway, it obviously is, because if we weren't here, there would be nothing to talk about. You know?
That's why I say consciousness. See the new one, and saying I mentioned briefly last time 5 dimensions, right? Consciousness is one of them. Environment contains everything else, the space, you know, all the 3-dimensional space. So that's another dimension. Then you have the world line, timeline, and also the state of the clock. See, it's a whole new thing. The whole new thing I'm talking about.
It's interesting. I think you definitely have to take it slowly, though, Rajan. You know, you need to be kind of be slow, methodical, and make sure you're not jumping ahead to any conclusions. But so I think maybe the observer, maybe this consciousness point is like 0 dimension, like or even 2 dimensions, depending on, or 3 dimensions, depending on the circumstances. But let's say, and the equation you're dealing with, let's say that the perspective point is going to be at an origin point. It's going to be like 0 dimensional. All the lines will cross over there, right? And create your projection. So that's where I think the consciousness or observer part should lie. What do you think?
Yeah, see that thing. You mentioned I had 2 presentation about the observer thing. I do the fundamental calculation. I go into the thing that the observer, if you're like a point, like infinity, and you see the earth, the whole universe as a point. If you go into infinity, right, the whole universe becomes like a point, and then you can manipulate that, but you cannot mix observer. I think that's the problem with
well, I'm going to stop you there, because how do we know that we can get so far away from the universe so it looks like a point? If the universe is infinite or non-orientatable within the 3-dimensional space, you're never going to be able to get out of it. You're never going to get far enough away from it to...
that's a de Sitter space and anti-de Sitter space, things like that you have to consider. But what I'm saying is that from a simple thing, suppose you are just driving, right? You are, so you are at a distance. You are looking at
the observable universe could become like a point. Or maybe if you had a 4-dimensional transformation of it, you could get it to a point.
Yeah.
If you're outside of the non-orientatable space, then there's no problem. You could make it a point. I don't know how useful that would be. I think it would be compressing a lot of information into a small point, and from a mathematical point of view, you could do something with that. I think it would be extremely low resolution,
Yeah.
I don't know. I mean, maybe it'd be interesting from the point of view of forces, but at this stage, you're now outside of the known universe. So I think if you're going to do something like that, you should write up a proposal maybe of like a page or two, just like explain the idea in a very like logical, easy, like the way like the way Manuel did with his hyperdrive and all of that. It was very speculative, but it was also very simple. Like it was very easy to understand. Exactly. I don't think it's probably not right. It's probably not provable. But at least it holds together cohesively, a bit like John's work that was like just all encompassing and just figured everything out and said it's all magnetic, or it's, you know what I mean? So John and Emmanuel's work are very similar in the fact that they try to be comprehensive. They try to include everything together. And even though they may not be right about everything, they might have some things completely wrong, obviously, because I think from John's point of view, and even like Wenzhang's and yourself to some degree, you would consider, but particularly John, because he's more of a traditional guy that art. No. Dang, I've forgotten his name. He's the guy who found all of these the pulsar or quasars, and they use them as these standard beacons in a sense of the Hubble expansion. Yeah.
Okay.
And then so they're really redshifted, so they're really far away. But Holton Arp, that's his name, and he's saying that no, these quasars, I think they're the quasars. Yeah, they are coming out of the galaxies. So the galaxies that we see are much closer to us than these quasars, according to cosmology. So they're less redshifted. So Holton Arp says, no, I've been looking at this stuff and I can see that there's chains of these quasars coming out of the galaxies. So that's like your source, you know, it's like spitting them out. And then he can even see them connected by like a cloud of like refractive dust or whatever, or just dust stuff. I mean, so it's clear that this quasar is connected in some way to this galaxy, and he found like loads of examples of these anomalies all over space, and did the general, what's the probability that the galaxy will have this little nodule on it that perfectly coincides with where the quasar is. And I think the odds of this happening multiple times were like billions to one. So these results were correct. The quasars and the galaxies exist in the same plane of the visible universe. And if this is correct, then our entire understanding of redshift and the size of the universe is incorrect, which would go towards the concept of a steady state universe where, for some reason, like redshifts have nothing to do with space expansion. They have nothing to do with distance, therefore nothing to do with the Big Bang or indeed the expansion of the universe. So that is pretty interesting. But I think recently there was some result from the James Webb Telescope which seems to help with the Big Bang model, and only the Big Bang could have explained this, and this is the claim. So I think from your side, there's a guy, have you heard of the YouTube channel called What the Math?
Who?
He's Anton Privyek or something. I think he's Russian.
Matu?
Anton.
Yeah,
check it out. It's like, what the math? Like, what the math?
What the math?
Yeah, that's the name of the YouTube channel.
What the math?
Right. So if you look at that,
M-A-T-H math. M-A-T-H math.
Yes, M-A-T-H. Yeah. So, and I think
it's mathematics or something. Okay.
It's mostly about cosmology and astronomy. And he's talking now. I'd have to watch the video again because it was a couple of weeks back. But he said that some effect that they found using the James Webb Telescope, which was predicted by the Big Bang model or falsifies the steady state model. And so I think like if you guys are going to push for a steady state model, these are the things you need to be aware of, and these are the things you need to be able to counter in your argumentation. So that's something to consider. I mean, it means like,
oh yeah,
if you're very invested in the steady state model, then you should be like, this should be like one of your main things. You need to be able to disprove what they're saying in order to continue with the model. So that's one thing. I mean, I was thinking of, John's work. It's, yeah, there was some funny thought I had anyway, because he believes in Holt and Arp's thing. So there's no way for him to use like redshifts to talk about the size of the universe, because, well, from the point of view of Holt and Arp's work, all of that is bunk anyway. It doesn't mean anything. There's some other reason for the redshifts, which is a fascinating prospect. But yeah, it just if that is the case, then it's just
oh yeah,
nobody knows. So it's pretty cool. Yeah, is there something else that we were talking about?
See, I think one of the things that nebulae, nebula, like Orion Nebula, things like that. I believe in that more. The whole universe like a nebula, and then in the nebula you can actually form black holes in there because there's a probability, right? That's why I consider, in the third paper, I think it's already proved it in the Canadian, in the CJ pass. And the fourth paper is still looking at it. So I will sometime talk about these papers. I think they kind of comprehensively, they talk, I'm talking about all the mechanisms there, but mainly a superluminous thing, right? Superluminar planum. I think the whole universe, I can agree with Emmanuel and John together. So, and myself, right? And you and everybody. But superluminar planum is the fundamental base, is the fundamental phase of the whole universe. The whole universe is superluminar planum. It's like a nebula, like a nebula. And in that one, you have monopods and things like that. So you have vectors all over the place, right? But at some point, the vectors can, there's also probability. If we are almost like infinitum, there's also probability somewhere the vectors will align themselves correctly. This is my whole thing. From random, how it become random to more ordered thing. Random disordered thing to become ordered. So disorder to order type of thing. Now you have to calculate entropy. I think I should be able to, because I always think, my thermodynamics is very high level. So I always, the back of a mind, the thermodynamics always plays out. So I think I should be able to rationalize that, but I have to look at the entropy, which is sometimes very complex, very complicated. But so the entropy, the problem is that disorder is connected with higher entropy, right? So initially it's an entropic universe. Was it entropic universe? That's the thing. Like you said, you have to prove that. One thing from superluminar planum is that it kind of assumes that it was highly, turbulent, which means it's entropic. It was entropic universe to start with. So that's a little bit harder, because was it like that? So that's something you have to think deeply, like you mentioned. But suppose we take it like that, so it was entropic, it was disorder. In that disorder, like a nebulae, right? Nebulae is more disordered. Inside that, because you have vectors, right? The monopole vectors are pointing out all over the place. They are randomly oriented. But at some point, local level, they start orient themselves the proper way because they want to form dipoles, right? So they orient themselves correctly, and you can prove it actually. Simple experiment that you have disordered vectors everywhere. You have to find the vector, right type of vector, entity that has the right type of vector, and you can
Okay.
say that, and then in the middle, somewhere in the middle, somewhere the local place, they start ordering themselves. The vectors start ordering themselves. Okay,
Right.
and
Yeah.
they start forming eventually the whole PDP mechanism that I am talking about. Eventually
Hmm.
the dipole eventually forms like a horde that John is talking about. They become like, he talks about like a permanent magnet, but the horde is like for me, it's like a two-dimensional thin film uh, of
Hmm.
of of the two north and south pole coming together, and they stick together. So they
Yeah, I'm
form.
not sure. I'm not sure if I mean, yeah, I don't know why. I think is there something a bit too complicated about it or something? It's
Yeah,
cool.
they become
There's
rigid.
some cool ideas there, and I mean, it's very interesting that you bring them all together. But at the same time, we have to think like, how likely is this?
No, I think you can prove it,
Yeah.
that if you have random things all over the place, right? At some
Yeah.
point, they will start to arrange themselves. That's the whole idea. They start
Oh
order them.
yeah, yeah. Well, then you're
That's the
talking
whole
about sort of
idea behind it.
order out of chaos, is it? And
Out of chaos, it was chaos. Yeah, exactly. It was chaos to start with, and from chaos you get order.
yeah, yeah.
How the
Well, I mean,
chaos to order.
this
That's the
is true,
proof.
right? You know, if you just like randomly hit a lump of metal with a hammer,
Yeah,
eventually it becomes magnetized. Or like if
yeah.
you were to bombard it with
That's
just
a good
noisy
point.
particles from all sides, it
Yeah,
eventually becomes magnetized because is the
the
average
stress,
the average of all of the bombardments is zero, or if you like, and
the stress. Yeah.
that's a
The idea is that.
specific vector in space, which means that everything aligns on that. I think you can do the same thing with the universe because if you look at the Milky Way, for example, or any body, and you look at the poles, the magnetic poles of all the stars are all aligned in the same direction. So that's weird. Why are they? You know, because they should be just all over the place. But I think somebody said, "Oh, you could just have all this random stuff, and it would just align them all in the same direction." Because, but I'm not sure if that's true. Is that true? I mean,
Yeah.
in order to do that, I think you'd need two blocks of metal, bombard them with the random noise, and then see are they aligned at the end of that experiment? Are they indifferent? If they're in different directions, then randomness did not account for the poles of the stars that we see aligned in the Milky Way galaxy and beyond. But if they are both aligned, if they're both like zero vectored north poles or something, well then yeah, I agree that the problem is solved. But so that's a
See the
worthwhile experiment to do. I don't know if that's something you could do at your college. I'm certain
Yeah.
probably.
One of the things you mentioned about the two metals coming together, right? They form interface. So what happens is that you are bang or anything you do like that, right? What happens? You are transferring the stress. Okay, the stress comes there, energy. Stress is stress tense energy, like energy tensor, stress tensor. They're very similar, right? So the stress will start coming, and they come at the interface between the two, right?
No,
Energy.
I think you might have misunderstood me a bit. I'm not talking about banging two bits of metal together. I,
Mm.
I think the idea is you put the piece of metal in like some sort of some sort of container, like a radiative container. Put it in there and you bombard it with particles, like
Ah,
high energy particles, just
okay,
all
okay.
randomly all the time. It's like the fuzziness on your TV screen kind of thing.
Yeah, yeah.
And then what you do is then you have a second running at the same time. You have a second box. You put a second piece of identical
Ah, separately. Okay.
metal in there, and you bombard them both with the same type of radiation at the same level. And then
Ah,
afterwards, you're supposed to take them out, and they'll both be magnetized, and they'll only have. But question is, will they be magnetized in the same direction? I suppose it would probably be magnetized along the length of the bar anyway. I mean, you're not going to get a magnet. Can you, like, if you have a lump of metal or something, can the magnetic field that's magnetized, I mean, can the magnetic field be in any direction, or does it?
It depends on the grains. What happens is there are, see, I taught one course also in ASU where I talk about magnetic domains. So inside like a ferrite or something, if you look at the inside microscopically, there are domains called magnetic domains. So the domains, you have the vectors in there, right? The magnetic pole vectors, they're aligned in certain way, right? So the domains, what happens is they're randomly aligned, randomly all over the place, that thing, right? In each domain. It's called magnet. Depends on the grain. Depends on the grain.
Before it's magnetized, they're all over the place.
Yeah, but it depends on the grain size.
They're all pointing in the same direction, yeah? Now the question is, if I have a sphere of metal and I magnetize it, it shouldn't matter where the pole is, because if it's a perfect sphere, there's no it's perfectly symmetrical. So the pole could be sticking out in any direction. If I have a block of metal, though, usually, like, if you get a bar magnet, the north pole is at one edge and the south pole is at the other edge. You never get a bar magnet where the magnetic field is aligned diagonally through the, you know.
That depends on the magnetic domain. See, the magnetic domain, you go inside each of the thing, right? They are like little things inside, right? Like grains almost. So it depends on the grain size, things like that. But you have like a little thing inside that, you have the domains. People are actually measured this. People actually microscopically looked at the domains. So they are separate domains. So they all look randomly. So in a normal thing, if it is aligned in some way in one domain, right? Magnetic domain. Domains are like less than micrometer, or probably less than that. Sub-micrometer, I think. I don't remember exactly the size of the domains, but they're like probably between nanometer and micrometer, I think. Somewhere in there.
What determines how the domains will become aligned magnetically? Is it the lattice structure of the metal? Or?
Yeah. So what happens is, so domains are all in each domain, it's looking at like that. But when you apply external magnetic field, the domains start aligning themselves. I mean,
well, they will align themselves in the direction of the external magnetic field.
Magnetic field.
Well, that's not disputed. That's a known fact. The question I'm asking now, we're dealing with a different situation where the metal is being bombarded, and let's say it is like just a block of metal. The metal is being bombarded from all sides. So there is no external magnetic field with unless there is. I mean, maybe this radiation has its own external magnetic field, and then it's just aligning with that. Well, if that's the case, then it has nothing to do with the randomness of the bombardment. It is from some sort of internally aligned magnetic field within the radiation. But that's not what they say. They say it's from the random bombardment. So if that's the case, if there's a random bombardment, I mean, obviously, if you take like the average of a random set of numbers, it's like 0, you know? It's like always the same, yeah? If you have like plus and minus values in there, it's going to be 0. So you would assume that this random bombardment would always produce an electric field, a magnetic field in the same direction. Would you agree with that?
Yeah. So let's look at it more closely. Let's analyze the whole thing. Okay, little bit. I mean, I'm not going to go too much detail, but let's look at it. You have inside a container. What is it? So there's only one block, right, inside, and the particles are. So I want to get it correctly. So I'm going to describe what I understand it, and you can correct me if I'm wrong.
Okay.
So you have a block inside a container, and you have somewhere in the middle, and you are bombarding with particles, right? And the block is being bombarded from all the sides by the particles, right?
Yes.
So I'm right so far, right? You can correct me. I'll go step by step, so you can correct me wherever I'm going wrong with your perspective, with your
Okay.
the whole what do you call the experiment. Uh,
Yeah.
so what happens is that you have, let's say, block. Let's say it's a cubic block, right? So you have 6 sides, 6 planes, right? The cubic.
Yes.
Okay. So you are bombarding all the 6 sides, right? So
Well,
what is happening?
I assume it's lying flat on a metal container, so it's not being bombarded at the bottom, is it?
At the bottom.
Unless the particles are going through something and bouncing them back up.
5 sides. Let's say it's hitting 5 sides.
Yeah,
so now you are heterogeneity.
Stand or something, but yeah. Okay, let's say 5.
Yeah.
At least
so
5.
Yeah. So let's do the first step. First step is you have heterogeneity because you have only 5 sides. The one side is not being hit. So you have already heterogeneity there. So let's look at what is happening. So you are saying it's not because it's random. There's no particular electric field. There's no external electric field or magnetic field. So it's mechanical.
I don't know. Yeah, we'll assume that that's the case. Yeah.
Okay. Let's say it's purely mechanical, right? So you have to consider what type of energy it is. So it's purely mechanical energy, right? Momentum transfer.
Yeah.
So you have, when it hits, it's going to transfer momentum or energy, right?
Yeah,
so
yeah.
It's mechanical energy. It's going to impart mechanical energy to each side, right? So you have stress form. So at the interface, you have to consider the interface between that one of the faces of the block and the environment, which is now the particles hitting, right?
Yes.
So
I agree.
So you have, let's say this is the surface, one of the surfaces, and you have the particles coming in. So at the interface, you have the particle and the phase interaction. That's called the interface. So it's transferring the momentum from here into the phase at the interface, right? So far, okay. So what happens? There are atoms there, right? Called surface atoms, right? The surface atoms. The surface atom is getting that stress sensor or that particular energy or the momentum, whatever you call it, right? They're all interconnected. Stress sensor is more like a pressure, more, for mathematical thing, but essentially it's transferring the momentum to that, okay? And Newton's law and things like that you can apply. So when it hits that, this is going to have a reaction force, things like that. But essentially it's transferring some of the momentum, and this atom is going to go down a little bit, right? On the surface. So then it transfers to the next atom, the lattice, let's say in the lattice.
Yes.
So like that. So it keeps going. The stress starts to keep going, right?
Yeah.
So at some point, what's happening is that the bottom one, there is nothing, right? So suppose it's a top surface. So it's going down.
Right. But if let's say the outside's getting magnetized, couldn't that align the inside of the arm?
Let's look at that before magnetization. Let's say what's happening, okay? As much as possible. I don't want to spend too much time on it, but the stress is traveling. So from this surface also the stress is traveling. From this surface, stress is transferring.
Yeah. I get your point. Yeah, it does seem like that the stress would diminish as you go deeper into the. You need more energy to get it into the center, right? Okay. I agree with that.
So you have 5 sides. The stress tensor, from the 5 sides coming in, all the stress coming together. Let's say it hits one of the magnetic domains, right? What is happening is transferring the momentum or the stress or the energy to that magnetic domain, right? So what happens is that whenever typically a random thing, you give energy to it, right? So it changes its configuration, so it can absorb that energy, right? When it absorbs the energy, it is order. See, order has higher energy. So you are supplying energy to that magnetic domain. Now how they utilize that energy is that they align themselves. because the energy of aligned thing is higher than random thing, right? You agree with that? Suppose you impart energy. Suppose everything is going around. Impart energy. They start aligning themselves because something that has higher order or configuration has higher energy. So you have to supply energy to make it more ordered.
Okay, yeah, I'll go with that. Yeah, why not?
You are disordered thing like liquid, right? Liquid,
like you were saying before, heat and entropy and all of that. Yeah, okay.
Yeah. So you can imagine very simple analogy. It's like liquid and solid, right? Suppose you're liquid, it's more disordered than solid. You agree?
Oh, of course.
Yeah. So you supply energy to the liquid, right? It can compress and it can form solid because it's more ordered. Because it has to absorb that energy. When it absorbs the energy.
Wait. Wouldn't you? You can't compress a liquid. If anything, you would take the energy out of a liquid to make it into a solid, cool it down. Whereas you heat the solid liquid.
Yeah,
so
cooling
you
down
is the energy to make less ordered materials, because that is how heat and entropy works. Remember, we were discussing that. If you apply the heat again to the water, you're going to create water vapor, which is even less structured again.
No, the energy, when I talk about heat, energy, it is opposite of heat. It's opposite of heat. Whenever I say heat, higher entropy. Energy is low entropy.
Oh, yeah.
So I apply less entropy to that thing, right?
Yeah.
To the high entropy. I am applying less entropy. Just think of energy and entropy are opposites. Very simple way.
Yeah. Okay.
High entropy means low energy. Low entropy means high energy. We can use that simple thing to avoid confusion.
Yeah, that's fair enough. Yeah.
Yeah. Whenever I say you impart energy means I'm giving less entropy. You see that? Lower energy. Whenever I say you apply heat means I'm giving you high entropy.
Yeah.
So very simple.
Very simple. And low energy then. High entropy, low energy.
Yeah.
Yeah. Okay. Yeah. I wasn't fully aware of that. I understood the concept of entropy and energy were linked, but I wasn't
entirely very simple. Yeah.
Yeah.
So I actually wanted to teach this course, and I would have, because I think from what I understand about that, I mean, that makes sense, and I did quite well those courses. I think professors agree with that. But they are not gone to the next level. Actually, I want to go to the next level. And even Sabina, if I have a chance to talk with her, I think I can, because I have pretty good background thermodynamics. I did well in undergraduate, graduate, and I wanna, I was competing with another professor from China. He was very good, but I did a little better than him. So I think I have better than average. I'm little above average in thermodynamics. I wouldn't say I'm the top level because I didn't have any chance to do, I was not a faculty to do that and then do research and things like that. But I have taught courses in thermodynamics. Normally, I wouldn't say 100% correct, more than 80% correct. Whatever I say. That's why I look at it overall thing. So you can correct me if I'm wrong. If you're like a student, if I'm teaching you or if I'm giving a lecture, I'll always tell students.
You know more about thermodynamics than I do. That's definitely not my area of research. So, okay. I mean, continue anyway. I think you're nearly towards the end, right?
Yeah. So the thing is that basically, so that's the analysis, right? So let's go back what happened. So essentially what I'm saying is that at stress, the magnetic domain can use to align themselves. It depends on,
so you're saying that the energy, you're saying there's this interface, energy is transferred into the block heterogeneously, ununiformly, but then the alignments happening at the top align what's inside. Is that what you're saying?
Yeah. So all the magnetic domains get some energy, right?
Yeah.
When it goes through different types of energy. Okay.
Yeah.
So that they can use, they absorb that energy. What will they do with that energy? They'll absorb the energy and then they will align themselves. There are conditions.
I mean, if you're just, let's say it is being bombarded by a load of particles, yeah, like just moving around, how is that energy and not heat?
That's a good point. I mean, so that's where the confusion comes. So that's where the difference comes. That's where the difference comes. If this is a low entropy energy, I'll call low entropy high entropy. Okay. So that makes it even easier. So let's say it's a low entropy energy, right? Then it can use it because it has useful work. See, you have to think that the idea of useful work is that it can do something with it, right?
Okay, so let's just go with that. Yeah. I mean, that was me just doing that. That was me being a bit cheeky, facetious, but yeah. So ultimately, you're saying that. I mean, are you saying that as the magnetic domains become aligned, they align other magnetic domains within the block?
They can. They have interaction.
Or are you not saying that? Are you saying something completely different? Because that's what I understood.
No. They're interconnected, but they can act independently also. Each magnetic domain can act independently.
Yeah, but that's what I'm saying. That they are acting like one is being aligned, and then it aligns another one. So it's
you can have
aligning. Yes. Yeah, is that what you're saying?
Yeah.
Okay. Because that's what I said. That's what I said like 10 minutes ago when you were talking. I was like, oh, so you mean this? And you didn't, I don't know if you answered, but you just kept talking. And then at the end of it, you kind of said what I said at the beginning. So, but you did, it was still interesting, Rajan. I liked it. And I learned about entropy and energy. So I definitely learned so. But I just thought it was funny because I also wanted to make sure that we were talking about the same thing. So to highlight that, I wanted to say that is what I said at the start.
Yeah.
To find out if you understood what I meant at the beginning as well.
Yeah. The reason I say is that the reason I say that one more thing is that not always the magnetic, we cannot assume that if you apply energy, it will automatically align and form magnetization. It won't do that. That's what I'm coming to the idea of magnetic domains. They can act independently also. They can also interact with other domains. But the fact that they can act independently means it depends on the type of energy. Like low entropy energy, they tend to do that. But there are some conditions to satisfy for them to align. So it won't automatically.
So what would you say the result of the experiment would be? You put two blocks in two different apparatus, subject them to the same bombardment level. When they pop out, when they're done, are they magnetically aligned in the same direction?
You cannot say for sure. It depends on two important factors: the material properties, like how the magnetic domains are.
The materials are the exact same. They're cut from the same block.
Exactly same. But I'm saying that.
But everything about the two experiments is exactly the same.
Exactly the same.
Everything about it exactly the same. Put them both in there. When you take them out, are they both aligned in the same direction or not? What's your
not necessarily? Not necessarily.
Not necessarily. Well, if that's the case, then you can't use that argument to say that. Not you now. I mean, the person who did initially use it to say that the reason why all the magnetic fields of all the stars in the universe, or in our galaxy at least, or in each galaxy, are aligned is because of random bombardments. Would you agree? Because I mean, in that case, the stars are all different anyway. There's
a little bit of give and take there, in the sense that if you do the experiment, you will find there will be a what you call a variation. What you call as the you do the experiment, you repeat the experiment. The best way to experiment is you do once, right? You repeat it few times, right?
Yeah.
Any experiment you have to do that, because you do this first time, then take it out, repeat the experiment, and then see, and you do the statistical analysis and see whether they all correlate, right? You will find the question is, are they within the 4 sigma level or 2 sigma level, whatever it is, where they fit into that thing, I think that's what you have to do with the stars also. They should do more than one observation, different observation, and look at that and see.
They've already determined that this is correct. that the
The
magnetic field,
random.
they're all aligned, and it's not a sigma 1 or 2 scenario. I think it's, maybe it is. I mean, maybe there's a statistical difference, and it's a sigma thing. Because isn't there? I think they found that a lot of, like, if you look in a certain direction in space, everything is rotating clockwise. But if you look in the opposite direction, everything is rotating anti-clockwise.
Oh,
But
yeah.
it's not everything. It's like a certain number, like a large amount. So it's most things are rotating in the same direction. So I assume in that sense you could apply a sigma value to that result. I'm not sure how useful that would be in general. Like what does the sigma value tell you? I suppose it tells you to a certain level of significance, but you could just use a percentage as well, you know? You just say, well, 80% of the galaxies are rotating the same way. But even, you know, like, doesn't matter. Well, it matters in the sense what the number is, because you would expect to be 50-50, yeah? But if it's like more than 50-50 to a degree, maybe of sigma level, then you're like, well, this is highly unlikely. This means that there's something going on. I also think it's interesting. So all of these galaxies seem to be going away. They're all redshifted, yeah?
Oh, yeah.
There's kind of big void between us and everything else. You know, there seems to be this gap.
Yeah.
Like our galaxy, and then nothing, and then everything. And then it goes out to, it's all going out. But in our local cluster, I think there are a couple of things that are moving towards us. So the only blue shifted galaxies are in our local cluster, and I'm assuming Andromeda would be in there, and then there's a couple of others. So anyway, so my theory, I don't know, this is probably pretty dumb, but so let's say there was again a 4-dimensional transformation going on in the universe, a bit like what we discovered in the LSTM and ANN imputation of the galactic SDS universe map. We found an area called the Great Attractor, which was very dense, and an area called the Great Repeller, where yeah, I can't remember what it. Yeah, Great Repeller, and that was very sparsely dense. And it just so happens that these two areas are like hidden behind the Milky Way, which is fine. And Gerd was saying, yeah, this fits in with my work about the toroidal universe in a sense, where it's constantly giving birth and dying, you know, which is interesting that this is also very similar to Manuel's model of the, and you know, the toroidal model of a electron has been floated around for a long time. But Emmanuel has a specific thing going on with his calculations, which is very interesting. But the point I'm trying to make is, so if we think of like a flipping tesseract, hypercube, that is a toroidal system as well, you know. The inner cube goes out, and then it inverts, and it comes back in and becomes the inner cube again. And that whole thing is a torus system, of course. So imagine, right, you have all the stars at the center of the galaxy, or center of the universe, then you expand it, and then when you get out to here where it's inverted, it's going to look like everything's moving away, yeah? Because
okay.
And that's the reason why there's this space, because our galaxy is in here, the space is the inside of the torus in a sense, and then outside are all of the stars. And the reason why they all look redshifted is because they're all projected out into infinity, right? Then when you rotate it, and then imagine, right, that the cube is rotating back in towards the center, yeah?
Okay.
Now, because of the way everything is, things on the edge of the cube appear close to us, but they're actually on the outside of the inner cube. If you think about it, when they're transformed in, they're going to be furthest away, whereas everything that's really far away is going to be at the center of the inner cube. The point is, I think I'm trying to make. I haven't, you know, I've studied this in a different context before, so trying to apply the same logical rules, but it's been a while, so I'm not a little bit rusty. But the point I'm making is that a small change in the transformation of the cube should affect the things on the outside first, or which is the outside of the outer cube, which is the inside kind of it. It gets confusing, right? So, but as they're moving in, so the things that are closest to us should appear blue shifted, right? But then once the whole universe kind of, and remember, you get the great repeller down here, so we're already seeing like the fact that the universe is shifting, great attractor. The whole thing will come together and snap back into the central box, right? The interesting thing would be to figure out at what speed will that happen at. It's like, because like they're looking into the universe now and they're looking at this side and they're saying, right, we're seeing galaxies moving at a certain rate. And then they look over here and they see, oh, these galaxies are moving at the same rate as these galaxies and in the same direction, which means they're connected gravitationally, the same force is affecting both of them. But if it's like this whole, like if it's all moving together and is eventually going to collapse, at what speed does that happen at? And because I would say it could appear to be moving very slowly, but as with these projective transformations, once they get past a certain point, they're going to speed up rapidly, and it'll all happen at once. So
it's like a black hole forms, like a black hole that forms.
Like the entire observable universe will basically smash into us, I think. Either that. Wait a second. Or what's here in the galaxy will expand into the vacant area and become the entire visible universe. So you'll have a new heaven and a new earth, essentially, which is what it says in the Bible. So I mean,
I think you are excellent at analysis of the geometry, because you know geometry very well, geometry of the universe.
Well, this is a theory now, but I mean, it's connected to Gerd's work, and it's connected. And it confirms what we've talked about. But also, it is a testable thing. Like we could, if we figured out the calculations for that, got the numbers, you could predict like how long we are away from that collapse.
The big collapse.
Yeah.
Crunch. They call it big crunch or something like that, right? The crunch.
Yeah, this is a different. This crunch is targeted right where we are. Like it's gonna, you know what I mean? I don't know what I don't know how I think if we're looking at the Big Bang model, everything is expanding from everywhere else. So when the collapse happens, I suppose it's going to appear like it's collapsing on us, yeah? Because from everyone's perspective, it's collapsing on them, right? So yeah, you could say it's big, kind of the same as the big crunch, although from this particular thing, there should be a direction from which the crunch will happen. So my guess is that it's either aligned with the great attractor or the flipping blue shifted galaxies should also be in some sense aligned with that great attractor. I don't know if that's true, but the point is that everything should come together in one region of the sky and then come towards us. So it'd be like, do you get me? It's all going to come together, blue shift, and then but by that stage, we might have already moved out the other side, So then we'll just go like expand and become the universe. That's testable though, because we could say, it's going to happen at this time in the future. You could be able to say, so you'd be able to say, this is the hypothesis, because it's definitely not a theory.
So many billion years, trillion years.
And it's going to take this long, and it's going to happen on this date. And if you're wrong, I suppose
billion years, who is going to know, right? After trillion years, we are saying after 500 billion, 20 billion years is going to happen. or on a tree.
Oh yeah, yeah. If it's something like
There's
that,
no
if it's
way to
1
test it. Nobody is going to,
no one would
uh,
try. But what if it
unless.
isn't? What if it was like a lot closer than that? Like, because
Oh
remember
yeah,
I said that. I mean, it's a bit like if you're shining a torch
uh,
far, far away.
yeah.
It looks like it's moving slowly. I think, against something. No, hard to say. So it's basically a projection thing.
Yeah.
Like once it's being projected out far, everything looks like it's moving slowly. But as it gets, as the thing gets closer to the center, it's going to go really fast. So it will be like an exponential thing. So it looks like we have all the time in the world and that everything's moving slowly.
Yeah.
But actually, that could change very rapidly. It could just go.
Actually,
that's what I think.
Acceleration factor. Yeah. The acceleration factor.
Yeah, you see, there would probably even be like traditional classical mechanical laws that you could calculate it that way. I'm thinking it'd probably be easier to. I'm just trying to think.
There are two things.
Yeah.
One of them is called capillary effect. The other one is Casimir effect. Okay, two things are there. So you have when you come, like you can actually test it. When they come close, there's something called capillary effect. You have negative pressure coming in, so they attract. So they become. I think a Casimir effect is very closely related. They will have Casimir effect. The Casimir.
Yeah, well, the Casimir is repelling.
Yeah. Two plates, like two plates are.
Yeah, I know, but
coming together. Yeah.
I don't know the other one. I know capillary action, which is water.
Capillary action, because you are like sipping, right? It's a capillary action. You have thin straw or something. You have capillary. You put it in there, very small hole. It will raise up. You will see that it's against anti-gravity almost. If you look at anti-gravity, it will raise up because of the negative pressure inside. You can calculate this. It's a very nice calculation of capillary effects.
Is capillary action also like if you were to put a thread into the water and the water is just soaking up the thread?
Yeah, up the thread. That's because of surface tension. Surface tension. There's a surface tension.
Related to that, yeah. Okay, so capillary action, and then you're not talking about that when you're referring to the Casimir effect, because that's happening on a much smaller scale, isn't it?
Yeah, they may be related at some point. One is mechanical, one is electromagnetic. So we have to find the connection between the two. So I'm not connecting right now. I think they may be related. I'm saying that they may be related.
I don't know. Yeah,
I'm not sure.
I'm not sure. But, yeah, it's interesting.
But the other thing I think I'm almost bought on this one. John's work especially is the source and sink aspect. So I would think that repeller will be like a source and the great attraction may be like a sink. I'm just thinking aloud. I'm not sure.
Yeah. Without a doubt.
Okay? So they come together because source sink also when you have source and sink, they try to connect with each other, right? Because low entropy, high entropy. If they can connect, there's a way to connect, they will connect. So
it might be that the source though and the sink are just not real things, in the sense that like the source was an event that happened in the past. Like how to describe it? Like if I were to pour this bottle of liquid down the sink, this is the source of the liquid.
Yeah.
And once I just dump it all into the sink, right? So it's all now in the sink flowing around.
Yeah.
The source is now empty. Yeah. And the actual sinkhole in the sink is being filled with water.
Yeah.
And then, and so it's all a process. But there is once the bottle is empty, we can just throw it away because it's no longer the source of anything. Because it's not an actual thing, So that I think it might be. It's not like an ongoing source. It just it's not even real.
It
From another
depletes itself.
perspective, if we were to rotate our perspective around, we are the source of the new galaxy, of the new universe.
Yeah.
You know, so something like that.
Sabina is talking very similar to what you're talking. But I think also we talk about let's continue. I think we can probably agree on low entropy energy, high entropy energy, right? So I think you can do even simple experiments like you are talking about drop. So the sink is high entropy energy, where your bottle is low entropy energy. Okay, so it always travels from low entropy energy to high entropy energy, right? So you are putting that, but the entropy, the high entropy of the sink changes once you put the thing. Its entropy now changes. It's no longer high entropy. It reduces entropy. It becomes an equilibrium.
Yeah.
Whereas your bottle, now it was low entropy, right? It's no longer low entropy energy. The bottle is high entropy. That's why you are throwing it away.
Yeah.
Okay. See.
Yeah, I mean, you can look at it that way, but it's not necessary to look at it that way, is it?
No, but then you
most
can.
Most people, when they do an activity like that, they're not going high entropy, low entropy.
Yeah,
you know,
I think
they're not thinking like that. There's no point.
You can quantify it.
Like their minds are working like at a higher level, at a faster kind of conceptual level. They just have the bottles empty.
Instinct.
Throw it in the bin.
Instinct.
Yeah,
that's an instinct. But I'm analyzing. I'm analyzing the instinct. I think it's a good analysis, a faster analysis with entropy, low entropy, high entropy. It's much faster, and you can quantify them. The idea is to quantify them, right?
Well, the question is, though, you know, if the concept you're using obscures the reality of what's actually happening, then it's not useful.
Yeah.
Only if it benefits, but if it's obscuring what's the actual geometry and what's actually happening in the system, then I think it either needs to be modified or just thrown out.
Modeling is like that.
You need to be careful that you're not confusing the situation because of the terms you're using. Because usually those terms are applied in a very specific way to like very specific things.
I agree.
I would say that this is a closed system, though. You know, so it's like
that's a good point. Open system, closed system. That's a good point.
This would be a perfectly closed system, I think, more or less. You know, I mean, there could be.
It's a closed system. See, system depends on how you consider the energy. You know, energy of a system is conserved, right? Conservation of energy applies.
Yes.
For any system.
Although there will be there are infinities involved in this closed system, so it's non-orientatable.
Because it's connected with the open system also. The air, the environment is connected with that. It's not. They are all interconnected, but the effect is very small.
The infinity is because it's a non-orientatable space. So the center of the cube, at the center, becomes the when you rotate it, that central point, which is just like a tiny point, like a non-dimensional point, becomes infinitely big once it's projected.
Exactly.
So, but if you were to rotate it, that infinitely big point again is just tiny. So, what was your question? Oh, so it's non-orientatable. So it contains infinities, though. So it's a closed system that contains infinities.
Yeah.
So that's something. I don't know if
So that's a good thing. Yeah. A lot of people who are considering geometry of the dynamics, I think you are doing something similar because you are more expertise on the geometry. You know, I look at more from abstract level, more from the thermodynamics and abstract level, where you are looking from geometry. I think you can combine it. That's an independent way to check it because it's very important. You know what you are saying. Correct me if I'm wrong. If you invert a point, you get infinity. If you invert a point, suppose a point, some kind of inversion, it creates infinity.
Yeah.
Right? From geometrical point of view.
Yes.
So that makes sense because how the inversion happens is what we have to look at. So that's the common point. our common point
Well,
of
it's not difficult. The inversion is not a problem. It's simple rotation. Once you rotate it, like if you have a projective, it happens all the time in projective geometry where a point goes from being within a circle and or within a radius and it's finite to it then moves to infinity. And when it's going to infinity, it goes rapidly. Like it starts, it's just normal speed, and then it goes boom, and then it goes so fast that it comes back the other side.
Back again.
Yeah. That means it's gone like.
Yeah, it's a simple algebra geometry, because essentially a point is like a zero, right? 1/0 is infinity.
That's the point I'm making about the outer the projected stars on the outside. They look like they're moving really slowly, but that's only because they're within the domain radius.
Oh,
once they cross the threshold, they're going to move like boom. It's going to be really fast. You get me?
It's like the capillary effect, and all these.
I don't think it's anything like I don't think it is anything like.
It's like acceleration. You can say acceleration because they get accelerated.
Yeah.
When they
it's like what I'm describing. It's the infinite projective point. Yeah. It's an infinite. It's like if
infinity becomes
like
zero.
The Riemann sphere. Yeah. When we project the Riemann sphere onto the tangent plane, tangent plane. You know what I'm talking about? In
like flat universe.
Yes,
like the flat.
Right. So you have the Riemann sphere, and if I take a point and I go up to the top of the Riemann sphere, that is going to be projected. Usually a point will be projected through the Riemann sphere onto the tangent. But if you're up at the top, you're going to be projected
parallel.
Yes, parallel. So that is the projected point at infinity. So just I'm just trying to be clear.
That's a good point. What you're making is a very excellent point.
Oh, yes, you understand that it's not capillary action. It is this thing. So when it's up here, it is projected everywhere. In space, just like the Heisenberg uncertainty principle. Like if it's up here, it's everywhere. If it's down here, we know exactly where it is, kind of thing. So it's everywhere, and then, but yeah, as the point, okay. So the analogy doesn't work beyond that. I don't think. Like as the point gets closer and closer. Well, I suppose I could show. Maybe I can. Maybe I can.
I know what you mean. They come together like that. Two surfaces, they're coming together. That surface is coming.
You're understanding the point I'm making about the projective point, and that's really the main thing. Yeah, because you can imagine. Well, think about it this way, Rajan. Even okay. Maybe I will share my screen though.
You're talking about surface versus the bulk, or the 3-dimensional versus 2-dimensional. So they become 2-dimensionally.
See this? See this thing? So let's say this is the Riemann sphere here. This is the tangent plane, and this red circle is you can see the circle goes around. Is projected onto the bottom of the sphere here. This red circle. So then, as this red circle, it's not projected onto the sphere. Sorry, it's on the sphere. It's being projected onto the tangent plane. So as this red circle expands, the blue circle on the sphere contracts, and then as it gets closer and closer to the top, which is the projective point, this red circle is going to expand at an infinite rate and fill the entire universe. And fill the entire tangent plane. So that's going to happen as this gets closer. Like it's moving at a constant speed, but as it gets closer and closer to the top, the rate at which this thing is going to expand is going to reach infinite speeds. So there's
like folding a 3-dimensional into 2-dimensional thing. You are folding and unfolding type of thing.
Kind of. I mean, I would
wrapping. You are wrapping there.
I'd be very careful about the words you use and how they inform your understanding of the geometry and what's going on. Because if you say folding or wrapping,
it's more like a
no,
net.
I would say no.
Actually,
I would
it's
say
more like a net. Actually,
rotations, projections. These are all fine words to use, but just be careful with your words, because not only will you could confuse yourself, but you will most definitely confuse others. So here's another example, actually.
no, what I'm saying, if folding is that suppose you take a paper, you fold it and you make a cube out of or a sphere out of that, right?
A what?
You take a
Sphere.
paper, you know, yeah, you can make a sphere, right?
Oh, a sphere out of a piece of paper. Well, I mean, technically, it's
like a ball. You make it like a ball.
If you see this, Rajan, like with the, if you have instead of projecting a square, sorry, circle, if you had a square on this surface and you projected it, it would look like, see the way this four-cornered object here is, that's actually a square being projected from a Riemann sphere. That it's like square within a square within a square, yeah? And there's some, it's all just made of noise as well. So this was my attempt at modular forms using this equation here, complex e to the power of 3 minus 1, and so on, and blah. It was a real nightmare. And then this is the other one, complex e to the power of 3 minus 1 squared, and then gives this, which is quite nice to look at. So this is the inverse of that one or something. But this is definitely like a wormhole, isn't it? You can change the ranges and the coefficients to get different kind of examples. But what I was really trying to do here was
actually your thing makes sense with the light. Suppose I am shining a light, right, on the sphere.
Yeah.
Okay. Suppose I'm looking at light. Suppose I have a sphere and shine the light. I think that's a better thing that I should probably correct myself. That you shining a light, and the light is like that. It forms like what you are saying, the red thing, the red circle, right? The light, as you move, the light moves like that, right? Then the red circle is going to expand.
Yeah.
Okay. And then at the top, the light is going to go like this. So that's why you're saying that it's going to infinity. Because at the top, then the light is going to go like that. And the shadow, you can call it shadow or whatever.
Exactly.
It's going to go to
infinity. You could even just, that's what I was trying to use the light earlier as an analogy. So let's say if I'm moving the light across the wall, across a wall that's like 5 feet away from me, and I'm moving it quite slowly, I think this works, then the light is going to track normally. But let's say the wall ends and then beyond that is like a load of buildings really far away. Then as I move my hand at the same speed, the light is going to track across those buildings way faster, I think.
Yeah.
So similar to that. So it's distance,
like a projection of light.
Distance is speed, but it's not actually moving faster. It's just an apparent thing based on perspective. So the whole thing is based on perspective, which I think is pretty interesting.
So the light, if you look at the light, how the light is shining.
What we're saying the whole time about perspective being a really important issue, and that was what that actual image of the Riemann sphere that I showed you is what I used to, it's the concept behind the uncertainty principle that I was talking about as well.
So I wonder whether Heisenberg is closely related to the light, this perspective and the light, what I'm describing about the light and the geometry, and the perspective, which is essentially perspective, right? Perspective is how the light is.
Yeah, I mean, exactly. They're saying that there is no connection between. What are they saying? There's no connection between the observer and the Heisenberg effect, because they really want to limit as much as possible this idea of an observer, because Well, I think they're just afraid of it because if they, you know, they want to keep consciousness out of it because then it implies that people are, you know, that basically the world isn't real. But they seem to be okay with. Well, I don't know if I'd say that, but it gives like people a pride of place almost in the universe. Then it seems to suggest that observers are important, consciousness is important, and they probably don't want that. And fair enough, probably complicates their whole.
Oh yeah, that's the whole thing. Yeah.
So yeah, so
But
then you have this, and this could be like you could have a double. What do you call that? A double cover of the sphere, because obviously the sphere is 4-dimensional. So as the blue sphere is contracting in one dimension, the blue, it's expanding in the other. Yeah. So you could imagine it expanding on this one, contracting on this one.
Okay.
So that could be interesting. And then, like, if we look here, we have a 4-dimensional coordinate system. Just let's pretend any 4-dimensional coordinate system. But if we're projecting down onto a 3-dimensional coordinate system, we can choose these 3 coordinates, or we can choose these 3 coordinates. You know, and we'll just get different. We'll just get a different perspective. We'll get either this universe's perspective or this universe.
So you're comparing flat universe versus a spherical universe or something like that.
Well, in this case, we're just looking at like the specific, like take for example the Heisenberg uncertainty principle. So down at the bottom here, where the sphere is touching the tangential plane,
yeah,
it is exact position of the particle. Let's say. So if we know the exact position, that means that this red circle becomes a tiny dot because the red indicates position.
Oh yeah. At the point of contact.
Right.
The point of the contact.
Yeah. So that means that the blue is like all the way in to the bottom, and so the blue is completely infinite. So we say that the momentum is infinitely uncertain. But as this grows, you know, this area becomes more uncertain. The position is more uncertain, so the momentum becomes more certain. But it might be better to flip it over to the other side, where maybe there is a different universe where, as the position becomes more certain here, it becomes less certain over there, or something like that.
Source sink, very similar to source sink type of thing.
Yeah, and also it implies that actually the position is not getting more or less uncertain. There is an exact value for the position. It's just, are we looking at it from here, or are we looking at it from here? You know? And then if we wanted to do like time-space coordinates, that's what I was thinking about. These would be all the space-like coordinates. But then time-like would be two space coordinates and one time. Let's say that would be your time-like. But I don't think that's what they mean. And besides, anyway, these are totally spatial coordinates. They're not. They aren't time-space coordinates. Although there is a relationship, because we have the GL23 or SL23 matrices, and then those also have some connection with tensor, don't they? There's a tensor matrices for all of these in the Riemann sphere and Lorentz transformations. So therefore, yeah, you know what I mean?
Yeah, it's a good thing. We should keep coming back to this, you know, because the geometry, you know, I think like we combine our thing.
Yeah, one thing
geometry. Entropic geometry. We should, I think that should be our main focus. I talk more about entropy, you talk more about geometry. I think we should combine, because geometry is something that will solidify our understanding. I
don't know. I don't like the word entropy though. Just, I mean, just because I think it has kind of negative connotations in
energetic geometry, energy geometry.
Yeah, it's interesting, isn't it? So yeah, we'll definitely we'll consider the name later on. But I like the idea of combining the two, like looking at it from maybe a classical physical
So
perspective as well as
because
geometric.
independent thing, and we can verify, because independent is like simultaneous equation, so you have independent way of, then you can come up with a common point. Whether we agree, come up with a common point is the key thing. If you're not coming with a
Well,
common point,
I think
then I think we have to keep
you
working.
probably wouldn't need a common point. Like, let's say if I just have, well, really, there's just the calculations. Can it be calculated? Can we come up with this precise prediction of when this is going to occur?
Exactly. Yeah, that's
and then,
the key thing.
So that would take a bit of mathematics, and that wouldn't be. That could be either very difficult or it could be like reasonably difficult. But the point is that you wouldn't. We know, as long as you understand what I've been saying, more or less. I think you do.
Yeah.
And you could just, without needing a common point, you understand what I'm saying, and then you have your classical equations. Let's say you simply apply those to the scenario, if you like. If it's something that interests you and you think it would be valuable, you could do that. Or you could work on trying to figure out exactly, make the prediction at what point in space and time, or time really, when will this occur? So I think that would be probably the most beneficial. It would also be, but I'm happy with, if you can describe it using equations to do with gravity or to do with entropy.
Yeah, that's what I'm coming up.
I think that would be fun.
Halfway. I am about 40% of the way. I think with all the formalism, I would say close to 40%. I don't want to overestimate, underestimate. I'll be close to 40%.
Yeah, well, now you might be talking about something else that I didn't consider. Like if you have a different theory that's, so you're not just applying normal classical physics to what I'm talking about. You're saying, oh no, I have my own separate theory.
Yeah.
In some sense, and then I'd need to apply that. Well, that could be difficult, because if your theory conflicts, or your hypothesis conflicts with my hypothesis, and they're just not compatible, or they don't, then that would be a problem. I would, So
that's what I'm talking.
I mean,
common
what
point.
I would suggest instead is to just, this is probably, just, you need to ask yourself, because you understand your theory or hypothesis better than I do. So you just need to ask yourself, does this apply in this situation? If not, then maybe I won't use that. And then you need to decide, well, then do I want to contribute to this at all? And that's up to you. But if you do contribute to it and your hypothesis has no connection, then you would have to just contribute based on the formalism that I'm describing here. Do you know what I mean? But if it turns out that your formalism does apply, then you've free reign to apply it. Do you get me?
Yeah. So
that would be how that would work.
Remember, I was calculating about the cell configuration, like a 30 cell, right? Example, you apply to 200 cell. Okay, that we can use, because that comes from my hypothesis. That's why I came up with the 30 cell.
Well,
right?
We could use that, but in a separate area, because this is, I think this is different. This is too different. Like, if you're going to bring that in,
astrophysics type of thing.
Yeah. This is, I mean, there's connections. It's not like totally unconnected, but I don't want to confuse people either. I want to keep everything nice and separate. If they can see the connections, like we'll point them out, but I'm not going to beat them over the head and like put everything into one bowl and mix it all until everyone just fucking goes crazy, because that's just not what I want to keep them nice and separate.
Yeah, that's a great thing. Yeah.
Sorry for cursing there. I'm Irish.
It's all right. Yeah, I was wondering how that comes about. You said Irish. Yeah, it's okay.
Okay, no problem. So so one thing was I had like the 200 200 and the 24 cell, and then so these are the coordinates for that, and then these are the bosons that are connected with the coordinates. But then I'm trying to rotate it so that it goes to the dual. So these are the dual coordinates, and they have the fermions. But there's no way, if you rotate these coordinates by, let's say, 45 degrees or even 90 degrees, you don't get these numbers, right? And if you take the joules of these or the joules of these, you don't get these numbers. So they've done some weird stuff here. They're taking, let's say this is 1, 2, 3, 4 dimensions. They call them 1 by JK, right? You know yourself, quaternions, yeah. And then they're taking like 2 of the dimensions here, so J and K, or 3 and 4, you know, JK, 1 by JK. They just take those 2 and then they divide by the square root of 2. And what they're doing there is saying, okay, here's your square, yeah, and this is the point, let's say, on the 24 cell, and then they're taking a slice through. Let's say this is J and this is K. Okay, these 2 planes, J, K. They take a slice through there, so that's why it's plus J.
Okay.
Plus J plus K, and then the divided, or the square root of 2 just is the midpoint of the line. Oh, sorry. So let's say this point is J, this point is K on the cube, and then the midpoint between J and K is that point, and that point is supposedly the square root of 2. But so that's what they're doing, and then they're doing that for every possible combination of IJK, 1 IJK and the minuses, and they do that for all of them, and then they get 24 new points, even though I think it should only be 23 if you do the maths. But anyway, that's how it works out. And so there is no way to transform between these coordinates to these coordinates because they're just simply different. So that's really annoying. So what I did instead was I just transposed. I just said, okay, these are all red, so they go to all of the red ones, you know? And I just tried my best that way. So this lines up the fermions with the bosons. So G1 is now equivalent to, what is this? The muon neutrino, the anti-muon, the muon anti-neutrino, the right-handed muon anti-neutrino. Okay?
Wow.
Yeah. Okay. And then this one is the right-handed tau antineutrino, and so on and so forth. And there's the left-handed electron is equivalent to the transformation of the 7th gluon, and so on and so forth. Now, these probably aren't exactly right, but they're just, this is just the best I can do because I can't transform between these 2 systems correctly. So it's just an approximation. And then over here, I'm trying to fit them all into, so there's the 24 cell, and there, the 24 cell can be described by S4 through its conjugacy groups, I believe.
What is the conjugacy of S4?
Yes, so S4 has 24 elements in it. 24 cell also has 24. I would probably need to show you that. So all the conjugacy groups, I think I have them written out here actually. But here, for instance, these are the conjugacy groups of S5. Yeah. Right. And so the point is that it is possible to relate S4 to, and remember, S4 is a symmetry group of a 3-dimensional object like a cube or an octagon or something like that. Or
what is S5? S5 is what?
Okay,
like
well, you see these numbers 1, 2, 3, 4, 5. S5 is just like every possible combination of those numbers. Same. Yeah, but that are also transformations that take different corners, let's say, of a 5-dimension or of a order 5 symmetry 5 object to each other, without changing anything. Same with S4. So like S4 is just I rubbed the numbers out, but let's say
1, 2, 3, 4.
Well, yeah, exactly.
S4 is like 1, 2, 3, 4.
Exactly, and this that should say S4, I think, on the top there. But let's say you go 3 to 4, so you go 1, 2, and then you switch 3 and 4 because 3 goes to 4 and 4 goes to 3. So now you have 1, 2, 4, 3. So that's one permutation. Here's another one: 1, 2, 3, 4. 1 goes to 2, so it becomes 2, 1, 3, 4, and so on and so forth. Yeah. So here's S4, and S4 can be related to S5, and S5 can be related to the conjugacy. This is the conjugacy group of this number. This is the conjugacy group of this number, and the number of conjugacy, the number of elements in each conjugacy group is related to the number of polytopes, subdimensional polytopes in the 600 cell via these relationships here. So the 12, this is each of these represents vertices in a icosahedron. No, sorry, dodecahedron, because it's 12.
12, yeah.
Yeah, the 20 is the icosahedron. So there's 20 of those, and then back to a dodecahedron. So it goes 1 point. Let's see, 1 point up here at the North Pole, then 12 for the dodecahedron, and one, and then more icosahedron, back to dodecahedron, whatever that is, a tricoctahedron or something. And I'd have to look that up. Back to dodecahedron. So that's your conjugacy groups goes 1, 12, 20. Or sorry, not conjugacy. This is latitude of the 600 cell. 1, 12, 20, 12, 30, 12, 20, 12, which is very close to the orders of the conjugacy groups, except there's a few that are just not, that are anomalous, like this, or
so they are the, I mean, they are like the almost like a trivial things solution. Yeah.
It's something
like degenerate or trivial. I don't know what we call it. Yeah, you get the same numbers.
Like look at this one. It's like 2, 2, 1.
Repeat.
That's out of place. And these two up here are also out of place. So the question is, right? So we can take these.
They're connected to particles. They are also connected to particles.
Yeah, the 2 Higgs bosons.
So the 20
the final one, and this one is the photon.
It's a photon. Why is photon? So
well, yeah, it's supposed to be gamma.
Gamma. Okay.
Yeah.
So that's a photon. Yeah.
That's a photon, and then so we can put all the color charges here, and then we'll have all the spins there, and then these will be. I'm putting them in by hand one at a time from this diagram. So it's really slow and really boring, and also really difficult. But
so you're doing something like quantum chromodynamics, very similar.
Right, because see, I can change all of the reds for greens and all of the greens for blues and so on. Just like in quantum chroma, you can like just transform them using SU2.
The color, the color
chart. Yeah. And so you can do the exact same with all of these as well. So once I start adding in the quarks, then the colors will become important from a charge point of view. But really, so far, I mean, I have to put them in for all of them. But once they're all in there, it's really it's only going to be applicable to the quarks, but still you have to put them in for all if you're putting them in for one. Also, the spins won't be applicable for the bosons, obviously, but that's just natural. I'm just going to put in zeros probably. Yeah, so that's it. So we have the how do you say this? The coordinates of the 24, which link to the symmetric group 4, which link with the conjugacy of itself. Sorry, which S4 links to S5. S5 has its own conjugacy group, which links to the 600 cells coordinates. So that's how, yeah, that's how we get from the 24 cell particles to 600 cells. Yeah, and then we want to go further. We want to go to the 120 cell, and then we can do some interesting stuff.
So can you?
Yeah. Oh yeah. Sorry. Just to keep that in mind, what you're going to ask. But just to finish up here, there's 24 particles. There's 24 coordinates in the 24 cell, but then there are 5. There's there's the fermions with the right-handed and left-handed spins, the charged fermion leptons. Then there's the quarks, and so, and with spin up and spin down. So that's together 5, and there's 5 24 cells in the 600 cell. So that's why we go. So then to apply these 5 24 cells, I just go, see the way this one starts with 1, and then this row here starts with 1, then it goes 5 4 5 3 5 2, and then this is all 2. So the first 24 cell I just go, right, anything with 1 is part of 1 24 cell. Yeah, the next 24 cell begins with 2. Yeah, and then the next one begins with 3. So I've done this because it's the simplest way of doing it, but it might not be correct, but it's like the fastest way of doing it. You know?
Okay.
So I mean, there's a logic to it, so it's made to work, but there might be a more correct version, let's say. And similarly, there might be a more correct version of applying the conjugacy groups to the polytope. I'm just using the most expedient version that I can think of. So all of this could be, the problem with doing stuff like this is that it's so big and, well, it's not huge, but it's big enough, to do by hand. And once you've done it, if it's wrong, you have to redo it.
Oh, yeah.
So,
but you have some methodology, so you can come back and then retune it or redial it.
Yeah, exactly. It's like a sketch. If I don't sketch it out now, I'll forget what I was doing to begin with.
Yeah.
So yeah. So does this so what were you going to ask, or do you have?
Yeah, my question is that based on the color, can you say it's fermion, boson, or quark based on this color? Can you put the color schemes to identify fermions from bosons to graviton?
Well, in general, I guess if the color is a charge, the charge will only apply to the quarks. So, but the color is uniform across the entire 600 cell. Well, when I say uniform, I mean it's applied uniformly. It is it's just, if you start coloring in the cells in the 600 cell, you go like red, green, blue in a certain pattern or whatever. You're going to fill all of the cells, and there will never be like 2 red cells together, 2 green cells. So it's a cycle throughout the entire thing.
You have to have different colors.
Yeah, they're all different colors. So, and then if you were to switch
the red and red won't go together. So in one cell you cannot have 2 red. Can you have 2 red in one cell?
No, because you can only color a cell one color at a time. You'll never have 2 cells next to each other that have the same color. It's like
so each cell has Like you have a red cell, you have a green cell, like that. Is it like that?
Yeah, you'd have like, think about if you had 3 cells around a single point,
Uh-huh.
because you have the vertices and the edges.
Uh-huh.
So single point, and then you're coloring in the cells or the faces around that point. It would go red, green, blue, and then the end of this edge connects to 2 more, which is another point, and then it will alternate. So it will go red, green, blue, green. Oh no, that's wrong. Red, green, or something. Anyway, however it works, it always alternates. The colors never you'll never have a red beside a red, or a blue beside a blue, or a green beside a green. And then you can switch all of them, so you can change all the reds for greens, all the greens for blues, and cycle them all that way. But the colors do not tell you which is a boson, which is a fermion.
That's all right.
Yeah. Is there anything that, the only thing that will tell you that, in fact, in a way, basically, I just have all of the bosons connected to one 24 cell in the 600 cell. And then the other 4 24 cells are split between spin up and spin down leptons, that's 2, and spin up and spin down quarks. So that's the other 2. And together that makes 5. That makes a 600 cell. Then you translate the 600 cell 5 more times, and you get the 120 cell. And why do we do that? I think at that point we just have, we therefore have enough to actually color in the quarks. But there's other reasons, we can then we can move into a hyperbolic space, or we can collapse the whole thing down into a Lobachevskian space and start doing some funky stuff just to see what happens, really.
So is there like a law? I mean, is it like a rule? Like, can you combine a red cell with a green cell, or you have to have a specific color for them to connect together? Like, some other red cells, can it combine with the blue cell, or can it combine only with yellow, some other yellow or some other color, but it cannot combine with green cell, for example? Is it like a rule like that?
I mean, not really. The thing is quite static in a way. Let's say the 600 cell or something, it's kind of static. The colors of the cells are just as you've colored them in, when you started coloring them in, based on the paradigm you use.
There's no particular logic of what
the
color there is.
Oh no, yeah, there is. There's of course a logic to it. It's a cycle. It goes. You just go red, green, blue, red, green, blue. Like you can see here, the even the 24 cell can be colored with 3 colors that are always separated by. You'll never have 2 blues together. Or
red, green, or RGB type thing. Okay.
Yeah. And then you could. So that's the reason why. Well, that's one of the reasons, let's say, why the 600 cell is 3 colorable. It's because it's made of 24 cells, which are 3 colorable. So, yeah. So anyway, so another a possibly more interesting answer to your question now is if we go from the 600 cell to the 120 cell, 120 cell, and move from that to, let's say, a hyperbolic space. So we're no longer in a convex 4-dimensional object. We're now in a hyperbolic, which is fills all of space in a 4-dimensional realm, because it has more than 360 degrees per rotation around an axis. So now, instead of just fitting 4 boxes around an axis, we're fitting 5. And because of that, we move from, well, actually, we just keep the dodecahedron shape, which is the cell in the 120 cell. But instead of having 3 of them around a an axis. We have 4. It's what I should have said. I said 4 instead of, I said 5 instead of 4. I should have said 4 instead of 3, right? Because you can only have 3 around a point in a convex polytope. Like take any dodecahedron, there's 3 pentagons around the vertices, yeah? Around each vertex.
Dodeca is 12, right? Dodeca, isn't it 12?
Right, so there's 12 pentagons in the dodecahedron, right? But each of those pentagons meet at 3 around the vertices, because what is the inner angle, or maybe not the inner angle, but the angle of the pentagon is, let's say, 120 degrees. So when you add 3 of them up, you probably get less than, because it's convex. Anyway, it works out. Like if you have 3, oh no, sorry, let's say in a hexagon, if you put 3 around an edge, and that's 120 degrees each, and you get 360. So hexagons can tile a flat plane, but they can't be wrapped around a convex sphere. So these are just things. So if we increase the amount of degrees we have around the vertices, we can fit more shapes in there. So if we could, if we increase the number of edges in the polytope from 6, from a hexagon, to 7, then it's going to naturally, instead of being round like a ball and then flat like a plane with the hexagons, it's going to curve outward in a hyperbolic sphere. But that's not really the point. The point is that we can go the other way then. We can like switch on, we can transform the dodecahedron into a cube for a start, right? And that will entail just moving some of the vertices so that they are in straight lines, and then we can color those different axes of the cubes, because obviously you'll have X, Y, Z in a cube, yeah, because that's what it is. So you can color those red, green, and blue, and then you can actually, with those axes, you can either have like this Lobachevskian space where those axes run in infinite directions, like the red, let's say the x-axes of the cube go forever in that direction and forever in that direction, and the y-axes go forever in that direction. So you're really just copying, pasting the cube throughout space all over the place.
So your x-axis will be red, y-axis will be green, and z-axis will be blue.
Right, like for example. Or you can switch them all around. It doesn't matter.
Yeah.
But then we can like delete all the other cubes, right? Because they're all just copies. Okay, and then we're left with one cube with certain number of axes. Then, and then you can like face those faces of the cube, which will bend the axes so that they join up. And at that point, but it will be green with green to make a circle, and red with red, and blue with blue, and then you'll have what they've already done all of this mathematics before. I'm just seeing where it'll lead.
Sounds very similar to Rubik's Cube type of thing.
Right. Yeah, actually that's a good, interesting point. And then the ultimate result is the Baronian rings. But the fact of the matter is you'll have compressed this entire 120 cell, which is 24, which is 600 cells compressed into a tiny cube, which is then compressed further into these 3 rings, which could represent, it would be a lot of energy, obviously, a lot of information in some weird, very compact form that can then rotate around itself, and then, geometrically what the heck is going on inside this thing, and what does it even mean for these forces to be all like sandwiched in there? It's just weird. It's a weird concept. It's fun though.
So 24 cell has more energy than the 600 cell?
Oh, no, I wouldn't say so, because there's 5 copies of the 24 cell in the 600 cell. So that would be 5 times more.
Oh, so it's like 5 copies of 24 cell and the 126 5 copies of the 600 cell. Is that right?
Yeah, I believe so. I believe so. Yeah.
So between 24 and 120, there's no direct connection. It's connected through the 600 cell.
As far as I know, yeah. Well, no, I wouldn't say no direct connection, because I think I'd have to look it up. It's been a while, but I think the 120 cell is weird because it contains like every polytope, pretty much.
So it is 24 cell is a subset of 120 cell in that sense, kind of.
Oh yeah. I think you could even construct a 24 cell, 120 cell out of 24 cells, but don't quote me. I'm not entirely sure. But yeah,
but they may not fit together, right? They may not fit.
I think they're supposed to, but you'd have, if you just check the Wikipedia page, it's pretty good. It tells you a lot about these things.
I mean, the 5 of 24 will not make 120, right? 5 24, only 5 600 makes it 120, right? Cell.
Oh, 5 24 cells will make a 600 cell. Yeah, and then 5 600 cells will make 120 cell.
So it's almost like 25. You need 25 of 24 cell. Almost.
Right. Yeah. So 5 by 5, right? And then
So 25 24 cell. 25 of the 24 cell probably can make 120 if they fit together.
Yes, that would be. I think that would be logical. Assuming my calculations are correct, I'm working completely off memory here. I think that's right. There is some disagreement online. Some people say 10, some people say 5, some people, but just based on my conclusions, I think it's 5, not 10. But I think you can do it in 2 different ways, so it looks like it's 10. Yeah. So that's, but I could be mixed up though. It might actually be 10 and not 5, but I'm pretty
because
sure
you have positive, negative, right? You have x-axis, positive x-axis, negative x-axis.
Yeah. Symmetric
so get,
transformations.
If you consider symmetry, you can get 10.
Yeah, it doesn't matter though. I mean, you could start at any point. So it's not just, it doesn't just fit in 5 times. It like fits in, or it doesn't just fit in twice. It could fit in like 24 times, in different rotations. So that's all irrelevant. Like, we don't want to get bogged down in that kind of, what's the most important point to start at? It doesn't matter. They're all the same, So just pick one. You just use that, and it's the same as any other one. So there's only one way to do it, as far as I'm concerned.
They're not arbitrary. Are they arbitrary? Not completely, right? They have some logic.
Well, like if you look at a cube and I say pick the topmost vertices of that cube. If there's no such thing as up and down in space, then there's no such thing as the topmost vertex. Any of them will do, because they're all the exact same, right? And when we look at the 24 cell or higher dimensions, like for instance here with the polytope, this was the North Pole, but that could be like you could literally select any vertices in the 600 cell and say that's the North Pole, and from that all of these characteristics flow the same as if you'd picked any other vertex. It's all the same.
That one on top, is it not the bottom one is the South Pole? Is it like that? The one all the way down?
Yeah.
The one here is the South Pole. Is it the South Pole?
-1, and this one is +1.
So North and South Pole.
Yeah, and they are connected to the Z boson and the Y boson. So the heaviest one, I think, and pretty much the lightest one.
Oh, so the Y or the gamma is the lightest.
Okay. And we use, do we use, feck it, no, we use These two make the Z boson, I think. Don't they? Two weak charge ones. They're really just they are, what do you call them? Direction axes, and then you have the photon.
They make strong.
They're the weak
strong
force.
boson. They're the weak force.
No,
but do they make strong boson, like a Higgs boson? It's like a Higgs boson.
Oh no, the Higgs boson is another
totally different.
pair of vertices as well.
But the Z.
Oh yeah. No, sorry. There's some bosons that are like these two guys or something, or the electromagnetic bosons, and then they create the coordinates of the Higgs doublet. But I've got like a Higgs quartet which collapses into Higgs doublet. You get me?
So W plus and W minus,
yeah,
they can make Z. Z is a strong boson, right?
No, Z is another weak.
It's a weak.
They're very heavy though. These are the heaviest.
Yeah, heavy.
The strong ones are the gluons. These guys. So
but the W plus W minus, are they massive or they don't have much mass?
Very heavy, yeah.
They're heavy?
Very. They're the heaviest particle.
So that's why Z is heavy.
Yeah.
Heavy boson.
And they're very heavy because they're very short-lived. In fact, they're basically quasi-particles, aren't they? Because they've never been observed, and they're kind of just there.
Oh yeah.
They're sort of there just to make the calculations work out.
Somebody got Nobel Prize, right? The weak theory.
I'd say so, yeah.
WC boson. Somebody got Nobel Prize for the WC boson also.
Yeah. Well, the Z boson was so named because it was meant to be the last particle that would ever be discovered.
But they discovered it, right?
Well, that's the question. Yeah, they did discover it, but I'm just thinking to myself, if you can't detect the W and the weak boson.
What's the spin? What is the spin of the W plus? Is it 1?
0.
Zero, right? Well, Z is 1, right?
Pretty sure it's 0.
Z is 0? Z?
I think so, yeah. Oh, I could be wrong.
Because the boson doesn't have to spin 1. Z boson means doesn't have to be spin 1.
Oh, right. Yeah, you know what? I've just been. I think I've been so distracted with my other work that I mean, I know graviton is spin 0, right?
Yeah.
Gluon is spin 0. Higgs is spin 0.
No fermions here, right? Okay.
Right, but you're right. The photon is spin 1, yeah?
Yeah.
So maybe you're right. Maybe these are spin 1. Oh, yeah. Okay.
They are all photons, right? W plus is also photon.
In a sense, no. I mean, I would call them the weak. They're combined with the weak force.
They're not fermions.
No, they're bosons.
Yeah.
But there's a big relationship between the Z boson. Z boson.
What is the difference between W plus, W minus, and Z? They're massive. Yeah. They are bosons, right? They're all bosons.
Yeah.
But what is the difference? Spin, I mean the left or right? What is the difference between W plus and W minus?
Right. Well, from a mathematical point of view, the W plus refers to an axis line in the plus direction, whereas the minus refers to an axis line in the minus direction.
About Z?
Then, yeah, I'm getting to Z. So if you think about an X and Y plane with so the X and Y axes, and then the Z axis is the electromagnetic
They're orthogonal. They're all orthogonal.
They're all orthogonal. So this is plus
Oh, I guess.
W minus, and then the z-axis is the photon, yeah, the electromagnetic axis, and then the z particle then is just like if I give you a coordinate in that particle space, weak space, then you get, let's say I say 3 plus boson plus 2 minus weak boson plus 4 electromagnetic, then that gives you a point, and that point is the z particle. It is a composite in a sense of the values.
So it's like a vector. It's like a magnetic moment or something that is pointing the x direction, y direction, and you combine it, it essentially forms the z thing, because you have electric and magnetic thing, and then the magnetic thing will be perpendicular to the electric thing, right? Electric. Suppose you have electric plane, the magnetic will be perpendicular. So z is like the magnetic vector, or the momentum vector is pointing in the z direction, something like that.
Right. So it's a vector boson.
Yeah.
So it means it would mean it would have to have spin 1, right?
Yeah, it should have spin because they're magnetic, right? They're magnetic spins.
Yep, I agree with that. That makes sense. So anyway, I mean, that sounds right to me. I'm gonna double check it anyway later on, but obviously 1, and I think all the gravitons have spin 0.
0, yeah.
Forgotten about the Higgs. I think they're spin 0.
They are 0, right? Higgs boson.
Yeah, because they're scalars, aren't they?
Yeah, they're scalars.
So they've got to be 0. Pretty sure.
How about gluon also?
Yeah, 0. Yeah, I think so. Anyway, if any of this is wrong, I can change it.
That would be great. If you can check that and let me know, I think I understand something.
Sure. Well, oh yeah. Well, certainly, yeah. Your how would you say it? Your breakdown of your
analysis.
Yeah. No, that's much better. I'm just using really lazy terminology. Analysis of the subject there was very interesting. The way you were talking at the perpendicular aspect and the vector.
Orthogonal.
Yeah. Orthogonality. Yeah, thanks. So those are interesting.
Yeah, they are just terms. Orthogonal means they are perpendicular. That's all.
Oh, yeah. Okay. So I'm gonna stop sharing that.
Just terminology. Yeah, that's what quite interesting. I think we should pursue that because I think it's important to connect with the standard model or particle physics, because that's what we know now, and what we are doing. That's what I'm doing that also, because what I want to know is that my formalism, does it take all the way, because it should not break up somewhere. But I think when I'm arguing this step by step, and it's a derivation, I think it's taking up me to the Calabi-Yau manifold, and that's how I can check whether I'm correct or wrong. I think if it takes to that level, then it's not wrong. That's the way I see it. But you have to still prove a lot of things. But it is at least the right path. See, it's like a decision tree, right? So you have, at each point, it's like a decision tree. So you can't go this way or that way, right? Yes or no. And then you go in that path, whether you go to the next one. If it is yes, then you go to, so like a decision tree. That's
You can have a derivation. There's another concept there of ontology, I think it's called.
Yeah, like an implicit flow chart. I'm using like an implicit for flow chart, like a matrix protocol. It's like implicit for flow chart. So I'm thinking, am I right in this one? Am I getting the thing? Then I go in that direction. If not, then you have to change and go to a different or change the hypothesis, whatever, and move to the
Well, I'm going to have to change this hypothesis. I just looked it up, and gluons are spin 1.
Which one?
Gluons.
Oh, that's what I was thinking. I was not sure.
Yeah.
Graviton is 0. We know graviton is 0.
Yeah, so everything else was right except for the one we got wrong was the gluon.
Oh, gluon has a spin, spin 1. So it's like a boson almost. It's like a boson almost.
Oh yeah, it is a boson.
Gluon is a boson. It's interesting.
Yeah. So what
gluon is like photon, huh? Oh wow. So gluon is like a photon. Wow. So in the Feynman diagram, you have the from the positron, the two fermions, the positron and the electron. Then it becomes through the mediation by the gamma, which is the photon. By the mediation, it creates two quark and anti-quark, right? And gluon. So the gluon maybe is taking from the mediator and getting that spin 1, and the two quarks, our the two quark and anti-quark, probably are getting the quarks. What is the spin of the quark?
It's 1/2. It's a fermion.
1/2 is like fermion. So the quarks are getting from the fermions the spin, and the gluon is getting the spin from the mediator. The mediator, which is a gamma, which is a photon. So yeah, that makes sense. So I'm thinking how that spin is getting transferred. Now I'm thinking that.
Yeah. It's interesting what you're saying. I'm not entirely sure I follow you. But,
the spin of the fermions is carried by the quark gets the spin of the fermions.
No, wait. Quark is a fermion.
Yeah. So see, the two fermions, the positron and electrons are fermions, right?
Positrons and electrons are fermions.
Fermions, right? Are they fermions?
Oh yeah.
So you have positive fermion and a negative fermion, right? Something like that.
Positive fermion. Oh, like you mean like
plus half minus half spin?
Yeah, it's you're basically talking matter antimatter then, aren't you? Charges.
Yeah, positron and electrons are antimatter. They're antiparticles, right?
Sorry, well, you can have the spin. The charges, if it's plus or minus charge, then it's antimatter. The spins can be. You could have like two matter, like electrons, with different spins. But then you could have a antimatter particle with an opposite spin to it. So positron is the antimatter of the electron.
Yeah.
They could both have the same spin.
They can have?
Well, they could both have. They can both have spin 1, for example, but still be antimatter, wouldn't they? Actually, that's an interesting question. Like, if two antimatter particles with different spins interact, they still annihilate each other. Or do they? Yeah, they do, obviously. But if they have the same spins, they annihilate each other. If they have the opposite spins, they annihilate each other. I wonder if the spins have anything to do with that kind of CP violation.
CPT.
Right. Yeah. I'd say that the people who were looking into that have already well thought about it and done the calculation.
They have done the calculation, yeah.
Because
your calculation that goes along with Feynman, I had to look at that. There is a calculation that goes with the Feynman diagram.
Are you talking about decision trees then in that sense, or in a different sense?
Yeah. So decision tree, a lot of things come together, So it is like different things have to match. So you are looking at different metrics and you see whether they all match. Because if they don't match, if they don't comply with each other, they're consistent, they comply with each other, there's a problem of compatibility. And that I looked into that. I checked whether it's compatible or not, And based on that, we want to generalize something, you have to look at the compatibility. You cannot just simply generalize something. So go to the next step. You see whether they are all compatible, and you check independently, and then you see they are all compatible, or they falsify or anything like that. Then you have to move a different part of the decision tree. You have to look at different way. So this is very time consuming, but I think it's important.
You
When
could
you do
program that. You program
formalism.
it.
Yeah.
You turn it into and I was thinking of doing that with something as well. I was like, it's very difficult to figure out like what coordinate is orthogonal to another coordinate.
Yeah.
And the other way you say, or the way they do it is to use the dot product. Yeah.
Yeah.
Because that gives you the cosine orthogonality or something. So
yeah.
if it's 90 degrees, if it's one.
Oh.
Oh yeah. But anyway, it doesn't really matter, because if I feed in a load of coordinates from, let's say, just a normal cube, and I say to the computer, all right, tell me which ones of these are orthogonal to one another. It will, let's say we have the point at the bottom of the cube here is 0, 0, 0. So 0 in all dimensions. And then the one over here is 0, 0, 1, because we've moved one space over in the x. And this one is 0, 0, 1, 0, because one space over.
Yeah.
And so on and so forth. Yeah, for all the other points in the cube. But like it will say that this point here is orthogonal to this point, and it's orthogonal to this point, and it's orthogonal to this point, and it's also orthogonal to the point on the far side of the diagonal.
It's a program that gives that answer.
Yeah. I just like ask it to calculate the dot product between all the other points in the cube.
Is it like an app or?
No, it's a simple program that I wrote in like 5 minutes or so. Right, less. So, but the point is, it should only tell me which coordinates are orthogonal, but it doesn't. It also tells me that coordinates which are along a diagonal, either on base or through the entire cube, it will say that they are also orthogonal, which is not true.
Not true.
So this
did you write this program?
Product telling you that coordinates are orthogonal is just incorrect, and that's really quite weird.
Annoying, yeah.
Unless mathematicians are using the term orthogonal in a way that no one else uses it. And
it should be perpendicular. I think orthogonal means they are perpendicular in general.
Right. You can't say something that is diagonal is perpendicular.
No, you can't.
Right.
No, two diagonals can be orthogonal if they are 90 degrees to each other. Only if they are. If that two diagonals, suppose one diagonal comes here, another diagonal comes here, and they are 90 degrees to each other.
Oh yeah. Well, that's a
but
fair
they have to be in the. See, there's a coplanar. They have to be in the same plane, because they are a skewed plane. They are in a skewed plane like this. They like a skewed plane. You cannot really say, because this angle is not two-dimensional. It's three-dimensional angle.
Well,
so that's more complicated.
Yeah, I agree. Okay, that's a valid point. But I think oftentimes when they're using orthogonality within four-dimensional structures, they're looking at it from the point of view of sphere packing. So they're very interested in this one, and this one are orthogonal. But like, let's say they are. And then this one up here is orthogonal. But they're like really interested in the Pythagorean theorem. So they want the diagonal, So then you have another one here. So the theory goes that you can pack one here, and then I think that's it. In three-dimensional space, you can't fit another sphere in between these two diagonal ones. But in the fourth dimension, you can. There's room enough to slot extra spheres inside the diagonals. So maybe that's why they don't care if the equation says the diagonals are orthogonal because they're happy to use orthogonal.
It will make more sense to me. There are 3 spheres, right? You connect the centers of the spheres, right? And that connection is perpendicular to the other connection. They can be said to be orthogonal. That makes sense to me. You know, the centers of, if you connect the centers and they are 90 degrees, right? Then they are orthogonal. That makes sense to me.
I agree.
But other than that, I don't know whether they're talking about tangent plane. That's more confusing. They're using a tangent plane, like a tangent to the surface of the sphere, right? A tangent plane to the surface.
No, they're just interested in diagonals, and Pythagoras they just used.
So they're connecting the centers. They're connecting only the centers of the sphere, right?
Yes.
I hope.
Yeah. You're right. Yes.
Yeah, then if they are orthogonal, that's okay.
If you do the calculation, if you do it the Pythagoras theorem, but for a 4-dimensional object, you will find that the diagonal line between the 2 points is twice as long as it is in 3 dimensions, which means that you can fit another sphere in there. Yeah, that's all the same.
That's interesting. I think we should continue this because I think, geometries, I believe geometry, that's the part I am not, because it's more this thing, but you are expert in that. So that's a good thing. We can combine the thing and check.
Yeah.
I'm
nerding out on the geometry and the hyper. You guys, you're nerding out on the algebra, the maths,
on the algebra and the field and all that thing. I mean the vortex field and the splitting of the vortex field and that kind of thing.
Yes.
I think we can combine. I mean, that formalism is almost over. So I am moving from there because I don't go to the next step until I can go back, because now I can retrace back to our original thing and I can check whether that's correct or wrong, the Helmholtz thing. That's what I'm doing now. And it seems to be fitting together, because there is a problem when I go back and then reset to that thing, whether they all dial back to the same thing or different thing. They all seem to be coming back. So I think that formalism seems to be complete in that sense, again, that's only 40% of the thing. The other 40% is your geometry. So you have 40 plus 40, 80. Then you have 20% left. And we have to figure out what that 20% is. That could be all those other things, God or Emmanuel, all those things come into picture. But I think, Emmanuel also has a lot of geometry in there. So
your 40% was to do with the
formalism.
And could you describe that again, just briefly, like you said?
Yeah, you start from the Helmholtz decomposition, right? That's where we start from. Myself and Emmanuel wrote that thing about vortex field and the gradient field, right? I presented in my the conference also. It starts from the point field. Just point. Point has a field. Point is not like Christian is saying. Point is not zero. It has a field, right?
Yes.
A point has a field. But that field can be split into 2 types of field. One is a gradient field. The other one is a vortex field, right?
Yeah, no question.
One is a vortex, is a rotating thing. The other one is just a gradient, linear. So that's where it starts from. That's the formalism. That's the basis of the formalism. The first principles.
You don't need to go all the way back to the start. I was just wondering.
Then you build up. You gauge it.
40. Yeah. Go on.
Yeah. You gauge it. You get string matrix. Something called string matrix. We did that together. You get a large expansion of the matrix. Okay. To include the electromagnetic field and also the mass, the Higgs mass field, the mass electromagnetic field, and the mass field. Okay,
I remember that.
Then you go to the next step. That's where I do the transforms, all the Lagrangian, all the Fourier. So I convert all of them into a time domain, rotation and time. in terms of
Yeah,
what the
this is
PDP.
where you lose me. This is where
Yeah,
I'm like,
the PDP
great,
thing,
no, good for you. Yeah,
the
good,
PDP
good.
audit. So
I
you have,
can't, yeah, I can't determine what, like, whether what you're saying after this point is correct because it's too.
yeah,
This is like too beyond my understanding.
yeah, because I didn't present the
I think a lot of
20-page
people would
derivation.
be a similar position to me, so that's
I agree.
that's
I
like a
agree.
level of understanding that you're looking at it from one perspective. And
Yeah,
most
the
people in the
reason,
world, well, obviously, I don't think anyone in the world probably knows exactly what you're talking about to you, because that's like a very common thing for
very
researchers.
few people who are reviewing, peer reviewing, they will understand. And to
Yeah,
some degree, Alexei will know a little more because I
yes,
had not, because he has been going through that. Not all of it, you know.
yeah. Oh, for
He
sure.
will
I
take,
know. I'm not saying. I'm saying like if you show your work to people,
yeah,
they'd be able to look at it. If they were to sit down and see the equation, they'd be able to follow it, I'm sure. But I mean, how many people have done that? You know?
yeah. In
Yeah.
conference, one guy that Shakir, he has gone through some of it. So the math
Yes.
part. So he knows.
Oh, sure.
That's why he's asking good questions. He asks about the space field and
Oh
everything.
yeah, Shakir from the conference.
Yeah,
Yeah, yeah. No, it'd be very interesting to get him to look at it and get his feedback because I mean,
yeah. He's
it
looking
would
into it.
be 'cause basically I can't do it. I can't sit down and look at your work and go, "That's right."
No.
That's
There's a one problem. That 20-page
you
derivation.
definitely need someone to peer review it and be like, you know,
Yeah. They have been doing that.
one way.
Whatever I'm saying, that most of it is peer reviewed, right? Most of the things, except the 20-page derivation, they take for granted that I am
Mhm.
correct. That will take
Okay.
a few sessions to go
Yeah.
through that pages.
Well, no, I mean, I would say like you're talking about 20 hours or something to go through that. Like,
Yeah,
just pick one transform and just do that one. Just so like instead of doing
yeah,
all of them, just do like one a little bit and just show
they're
like I
interconnected.
just want to I don't like I just want to see the logic. It's not like I'm questioning whether you're right or wrong.
Maybe initial part, I can show you the initial part
Yeah, I
because
just want to
what happened?
see
Yeah,
some cool maths. I'm not and learn a bit. You know,
yeah,
I'm
the
not
initial
interested
part.
in like,
Yeah,
I'm not interested in figure out like, oh, is everything you're doing correct? I just want to know how it's done.
yeah.
If it's just
Sampling.
like an example, like that's all.
Yeah,
It doesn't have to be.
yeah,
I'm not going to sit through 20-hour derivation.
yeah,
Are you mad?
yeah. I'm saying that. Yeah, I mean saying that in the initial part I can show where I start from,
Yeah,
and then show that, and then say, okay, get to the other one.
yeah. Just show us
So
something cool. Like, show me
yeah.
your process.
Next time,
Maybe
then I think we are almost today. I think we are almost over the limit to some degree. But
they're
next
done.
week, I can probably show the first simple part, the first first part where they use the transform, right? Uh, the first part of the 20 page, the first 2 pages, 1 or 2 pages of the 20 page, I can show something like that. I'll try to work out, and then I'll try to work out that separately also. But I don't know. I have to see how to do that. See what I like in that's why Hawaii conference or World conference will be useful. One screen, okay, I'll show my work, right? The other screen I'll work it out, you know, like in the blackboard, like in classroom, like info room. So one screen will be just showing my result, right? The other screen I'll work out how I arrive at that result. That's what I like to show. But
Oh
I
yeah.
don't know whether I can do it here. So so in a classroom or in a setting, we can do that very easily, that's what I want to come up with. That's why I want to present in like a Hawaii thing. We can go over that, or World University. Once we have that,
Mhm.
we can go over these. Like in a classroom, we can go, and then step by step we can go. But
Yeah,
we'll
well,
see.
what you could do there, Rajan, is like what I was doing when I was sharing my screen. On one side, I had a document open up in Word, and on the other side, I had a document open in
Yeah.
numbers, like kind of Excel. So you just split your screen, and on one side you have an image with the results.
Yeah, I will see.
On the other side you have like Paint or a whiteboard app or some sort of layout editor, and just type away. Okay, obviously you need to go there, Rajan, and so I'm not going to hold you up any longer.
Next week. We'll try something next week. Yeah, we'll try something next week. See how it works out. I'll try to see how we can